Hi, I'm Yu Cong at Tokyo Tech. I will be talking about a variation of refinement types that can be used for counterpoint composition and beyond. Refinement types are a powerful tool for expressing program specifications. Hi, I'm Yu Cong at Tokyo Tech. I will be talking about a variation of refinement. Hi, I'm Yu Cong at Tokyo Tech. I will be talking about a variation of refinement types that can be used for counterpoint composition and beyond. Refinement types are a powerful tool for expressing program specifications. A refinement type consists of a base type, which describes the shape of an expression, and a refinement, which is a sequence of predicates describing the detailed properties of the expression. As an example, suppose we would like to define a type tau representing a non-empty list of integers whose head is a non-zero number. Such a type can be represented as a refinement type whose base type is list_int and whose refinement is a conjunction of the non-empty and non-zero head requirements. Under this definition, a refinement type checker will tell us that list123 is an inhabitant of type tau, but list012 is not. In a traditional refinement type system, refinement predicates are uniformly treated as mandatory requirements. This is reasonable in situations where we use refinement types to describe specifications of programs, because for a program to be correct, it must fully meet its specification. However, the uniform treatment is problematic in situations where we use refinement types to describe specifications of music, since music has a rather vague notion of correctness. For example, when writing a melody in the style of the common practice period, it is preferred but not required to start and end with a tonic note, where the tonic is the first note of a scale. So in the specification of a C major melody, we would have two predicates representing non-mandatory requirements. Correspondingly, when deciding whether a melody is good or not, we would make a graded judgment rather than binary one. To express vague correctness of music, I propose weighted refinement types. The idea is to associate every refinement predicate with a weight representing the importance of that predicate. By building a type system based on this idea, we can guarantee musical soundness, that is, highly weighted music does not sound wrong. So far, I've developed a weighted refinement type system for composing species counterpoint, and that is the main result I would like to share with you today. Okay, so species counterpoint was developed by Johann Joseph Fuchs as a method for teaching multi-voiced composition. There are 5 species of counterpoint differing in the complexity of the rhythmic structure. Among them, we are going to focus on the first species, which is the simplest one. Here is an example of 2-voice first species counterpoint. On the bottom, we have a fixed melody called cantus firmus, and on the top, we have a counterpoint line. As you can see, both voices have exactly one whole note in each bar. Counterpoint has a set of rules, including mandatory ones and non-mandatory ones. This example adheres to both groups of rules, so you should find it well-sounding. Now, let's look at some examples that break the rules. This example breaks 2 rules that are mandatory. I believe that you all found this example not as good as the previous one. So what is wrong with it? The first problem is that it uses a fourth interval, which is considered dissonant. In first species counterpoint, dissonant intervals cannot be used anywhere in the composition. The second problem is that it has a direct fifth, that is, a fifth interval that appears in a context where the two voices move in the same direction. In counterpoint composition, direct fifth and octave are strictly prohibited. We next listen to an example that breaks a non-mandatory rule. This example sounds odd, but probably not as bad as the previous one. The issue is that we have a chromatic note, a note that is not a member of the C major, in the counterpoint line. Chromatic notes are allowed in counterpoint, but they do not make sense in all contexts, so they are generally not preferred. And here is another example that breaks a non-mandatory rule. Again, the counterpoint doesn't sound great, although it is not too bad. The issue is that we have repeated notes in the counterpoint line. Like chromatic notes, repeated notes are not disallowed, but they tend to make the composition boring, so they are not recommended. That's some of the basic rules of first species counterpoint, and I designed a language in which we can reason about the correctness of counterpoint using types. In this language, counterpoint is represented as a non-empty snug list, and each bar is a tuple of a pitch and one or more intervals. The composition rules are represented in the form of a weighted refinement type. So here is the list representation of our first counterpoint example. It is constructed from left to right by extending the singleton list of the first bar with subsequent bars. The elements of the list are pitch interval pairs, where the pitch is a note in the cantus firmus, and the interval is the distance between the two notes in the bar. And here is the type representation of composition rules. It is a weighted refinement type that has two groups of refinement predicates. These predicates encode rules on a single bar and rules on two adjacent bars, respectively. The weights on the predicates represent the reward or penalty. In particular, when the weight of a predicate is minus infinity, the predicate represents a mandatory requirement. With these design principles in mind, we can interpret the type here in a straightforward manner. The first group of predicates prohibits dissonance, encourages imperfect consonants, and discourages chromatic notes. The second group prohibits direct fifth and octave, encourages contrary motion, and discourages repeated notes. Having seen the representation of counterpoint and its rules, we look at the typing rules that connect these representations. In our language, we use a special typing judgment for lists, which has a weight telling us how correct the counterpoint is. To see how the weight is computed, let's observe the rule for typing a singleton list containing an expression E. Here, we check which predicates in the first group, psi 1, are satisfied by E, and sum up the weights of those predicates. We then use the sum W1 as the degree of correctness of the singleton list. The rule for an extended list is similar. Here, we additionally use the second group of predicates, psi 2, to evaluate the progression from the previous bar to the newly added bar. And we include the sum W2 in the total weight in the conclusion. One thing I would like to note here is that proper evaluation of counterpoint is much more complex, but for now, we just take this simple additive approach. Okay, so let me show you how the typing rules work for our counterpoint examples. This is the most correct one. On the top, we have the weights associated with rules on individual bars, and on the bottom, we have weights associated with rules on adjacent bars. Since this example does not break any rules, the summands are all positive numbers. We next look at a bad example. This example has a dissonant interval and a direct fifth, which are both prohibited and thus associated with a minus infinity weight. Therefore, the overall weight is also minus infinity. Now we type an OK example. This example uses a chromatic note, which is not preferred and hence has a small penalty. So the overall weight is positive, but it is lower than the weight of the first example. From these examples, we can conclude that although our evaluation is naive, it gives a higher weight to better counterpoint. So our type system is consistent with the slogan, highly weighted music does not sound wrong. Okay, so far I have talked about how to use weighted refinement types to evaluate counterpoint. At future work, we intend to use this idea to synthesize counterpoint. We believe that this can be done by extending existing type-directed synthesis techniques with weights. In addition to this, we would like to explore programming languages' applications of weighted refinement types. A possible application would be optimization problems, like the famous ski rental problem, where we have various weighted constraints. Using weighted refinement types, we might be able to express those constraints at the level of types and thus ensure the optimality of the computed solution. Okay, so in this work, I proposed an extension of refinement types that is useful for counterpoint composition and potentially for programming as well. What we can learn from this is that a type theorist may get inspirations from a non-programming domain, like music and other kinds of art. I believe that the firm community will discover more interesting type systems in the future, and I look forward to learning about your discoveries in the future editions of the workshop. Thank you.
Hi, my name is Alistair. I'm going to be talking today about a functional EDSL for mathematics visualization.
Hello? Oh, all right. I think we needed a minute or two to readjust the sound. Is that correct? Okay, so please think of your questions for a second, and we'll get Yu attached. She's online, but we need to fix up the sound.
Yo, can you hear us? Great. Okay, cool. I think we're good to go.
All right. Are there any questions?
Hi, Yo-Yo. This is Steve Taylor from Illinois. I just have a couple little questions about the counterpoint rules. In the example you have with the A flat, with in the first species where it's like A flat to B to C. When I learned counterpoint, if you had an interval of a augmented second, that I think that would be negative infinity just for me.
So in my current implementation, I just treat the A flat. So we don't distinguish between is it minor third?
It sounds like
And
a minor third, but it's spelled like an augmented second.
yes, we don't distinguish between them.
Oh, okay, okay. Well, never
Yes.
mind then. Yeah, sorry. That's it. Neat. I liked it.
Mhm.
Hi, Yo-Yo. Audrey So, University of Washington.
Mhm.
I'm just curious, what would be the benefit of using, like, also very cool work, but I'm just wondering what would be the benefit of using, weighted refinement types and type-directed synthesis versus something like, I don't know, MaxSat or, other, SAT, like, optimization techniques.
Mhm. Yeah. So the benefit is that in my approach, we can statically guarantee the kind of correctness of counterpoint, right? Because we have all the constraints at the level of types. If we just implement these constraints at the level of terms, then you can't view the counterpoint as the proof that it is correct.
Okay. Yeah, thank you.
Thank you.
Hi, Yu. May, we've talked a lot. I was curious if you have any answers for counterpoint rules that require looking at more than single intervals at a time. For example, the famous horn fifth does allow you to approach a fifth by parallel motion, but that's just because it's so dang cool when it resolves in the next step. Is that something that your system can take into account?
Can you repeat your question?
So horn fifths. Let me take my mask off 1 sec. It's a very muffling mask. My apologies. The horn fifth is a sort of classic counterpoint maneuver where we're in the middle of it. We're going to approach a fifth, an interval of a fifth, by parallel motion, which normally would be banned in traditional counterpoint rules, but is usually added as an exception because people liked it even in the 16th century. This has an interesting character because you actually need to look at the approach and the resolution in order to determine whether that should be weighted as positively or negatively. Is that something you can encode in your system?
I didn't know that rule, but I think if we can extend the rule for extending lists to look at a more global structure, maybe we can handle that kind of constraints.
Thanks.
Thank you.
Hi, Yu. I'm Charlotte. I'm from Worcester Polytechnic Institute, and I was just wondering. So counterpoint obviously is a very strict set of rules that are, and there are absolutes. But in many other styles of music, even classical outside of counterpoint, you know, contemporary music and especially jazz is defined often by its rule breaking. And I was wondering if your system could instead be modified to kind of reverse the rules and see, like, does this actually meet some kind of negative requirements? Like, does it not have too much harmony?
Yeah, that's an interesting question. So far, I'm just considering this very strict setting. And I'm not sure if my approach is good for those kind of more contemporary compositions. But I'm interested in exploring that.
Thank you.
Hi, you may again. Sort of in the vein of the last question, I'm wondering if your weights are configurable, if I could easily take your system and adapt it by changing the rules a little. Let's say instead of being Palestrina, I wanted to be Carlo Gesualdo.
I think that would be easy. So currently, in my system, we need to manually adjust the weights of various predicates, and you just change the weights, and then you will get a different rule system.
Awesome, thanks. We still have a couple of minutes. More questions.
Hi, Yo-Yo. Really cool work. Thank you. I'm Amy from the University of Washington. I know you just said that you didn't really think about other types of contemporary composition when you were designing this, but I was really curious to learn if you had used your rules to try to weight different pieces of music, like if you had taken known counterpoint works and taken their weights and maybe compared them with the weights of other types of works. And I'd be curious, especially to hear if you could detect a sort of adhesion to the counterpoint rules or sort of counterpoint-ness in works that are not, designed with counterpoint in mind. And all this just to say, have you tried evaluating or getting scores for pieces of music that have already been composed?
So so far I have just tried strict counterpoint. Let's see. So I don't know. This is part of my future work, I guess. I think there's a lot of work on composing other genre of music in the machine learning community, and I believe that they still use some kind of weights for that line of work. So I can probably borrow some ideas from that kind of work.
Thank you.
Hey, Yu, I promise I'm not trying to ask every other question. And we do have 5 minutes, so plenty more time for questions if any people find late breaking. I'm not sure if we have a way to ask questions online. But if we do, we should check there to see if there are any. So if you're on Discord and wondering why we haven't gotten to you, we forgot to look. Our apologies. I have a question about the various species of counterpoint, and in particular, the weighting. So in addition to their different aesthetic qualities, there are just literally more intervals in species 2 or 3 counterpoints. Do you have a way of sort of weighting the program so that I get a score that is based on the overall goodness, but not influenced by the length, not influenced by the actual number of intervals in the program?
I don't think I understand the question.
Well, it looks like it's a straight addition right now. So if I had a perfect species 1 counterpoint composition, and then I added 2 more measures, the score would go up. Is that right?
Yes.
But if I'm comparing 2 pieces of counterpoints and I want to know which one's more idiomatic, the length of the piece tends not to matter for whether it is idiomatic or not.
No, but there are some rules specifically for the beginning and the ending.
That's certainly true. I'm just wondering if it would be easy to convert the system so that the score is invariant with respect to the number of measures in the middle. If I add 3 measures in the middle of perfect counterpoint, I don't change my score if it was already perfect.
Yeah. So in that case, maybe my current list-based approach doesn't work very well. I think John has some thoughts about that, so we can ask him.
I talk to John sometimes, so yeah, I can do that. Thank you.
Yeah.
All right, we have one question on the Discord from Liao Xia. It says, what might a more elaborate weighting scheme than adding weights look like?
Elaborating weighting scheme. I'm not sure what it means.
All right, maybe if Liao can add something to the question to explain it a bit more. Meanwhile, as we have a couple minutes, I do want to say I've worked with you before, and of course looked at her current work, and I maybe she's being a bit modest, but I think for a lot of these extensions and handling more contemporary stuff, I believe it's definitely doable in our system. Once you handle higher species counterpoint, you're already looking at more global things, so that will handle some of May's things, and I think the contemporary music and so forth can be handled by adjusting weights in different ways. So I do believe this has a lot of promise for more advanced use as well.
Thank you.
All right, so it looks like Liao is typing in something here, which hopefully we'll see soon in a second. There's another question in the meantime.
Hi, Matthew Lutzi, Aarhus University, Denmark. I'd like to know if you've thought about how to integrate this with music composition software to act as kind of a linter for composers.
Wow. So initially, I was trying to extend the Synquit synthesizer, which uses refinement types to synthesize functional programs. So I wanted to extend that system with weights and compose music. But yeah, it would be interesting to create something that can actually help people compose correct counterpoint.
Thank you.
Okay, I see the Yao's text.
All right, do you see the question? So he says that you mentioned that you just added weights together, and that was probably simplistic. I was wondering if you had already had some thought into more realistic rules to evaluate counterpoint.
Yeah, so there is a study on using dominance relation for composing counterpoint. I still don't fully understand that work, but that is a more kind of realistic or serious evaluation of counterpoint quality. So one way to do that is to encode their rules as types.
All right, I think we're out of time, but I think it's, 1 a.m. or 2 a.m. there in Tokyo. So thanks very much, Yu, for staying up late to answer all of the questions. Wonderful questions for everybody. Fantastic talk. Let's thank you for her talk.
Thank you.
All right, and I hope you get a good night's sleep.
Yeah,
all right.
Good night.
Thanks very much. All right, so we have our next talk by Ivan Perez on functional reactive programming. I think Ivan wins the award for most talks in one day. This is his first of 3 today, and plus he had an experience report at ICFP earlier, so I'm glad we get him when he's nice and fresh. So take it away.
First, let's do this. Can you hear me? Yeah. All right. Can anybody let me know when I have about 10 minutes left? Can someone keep an eye on the... Yeah. I tend to lose track of time. Maybe 5 minutes? Sure. Okay. All right. So thanks everybody for making it, for being here and staying till Farm. It's a pleasure to be back at Farm. And today I want to talk about functional reactive animation, the way that it was kind of envisioned originally. And kind of bring everybody back to the original concepts. So probably many of you have heard the concept or the term FRP, functional reactive programming. And that's an idea that was kind of came to be around the 90s, mid-90s. And FRP is an abstraction to describe systems that vary over time. And over the years, the term was kind of diluted and used to describe systems that were not necessarily over continuous time, not necessarily functional, They didn't have the notational semantics, and kind of the term lost its meaning. But FRP, at its core, is a temporal framework. The keyword in FRP is missing. The keyword in FRP is time. FRP is about time, and FRP is about meaning. It's about focusing on what you mean to say, and the meaning of things, and the denotation. And over the years, there have been tons of libraries. This is first page, I think, of 3 of FRP libraries on Hackage, the Haskell package database. And it's very easy to create your own. It's very easy to create your own library. I think the core components of an FRP implementation are about, I think it's just 8 primitives and combinators. So it's very tempting to create a new one. And there have been, when I started my PhD, I counted up to 50 implementations that were in the wild. And these implementations get abandoned. People move on, they do other things. So if you start using one of them and learn one of them, chances are your code in a few years is not going to work anymore because nobody's maintaining that library. And they don't necessarily follow, as I said, the principles of FRP as originally imagined. And people get confused. This is a very common question on Stack Overflow. People saying, how do I make sense of this ecosystem, right? So much so that one of the most popular FRP projects is called the FRP Zoo, which just tries to help people make sense of the ecosystem and explain a few examples how you would write them in different implementations, right? And this is kind of like the landscape of all of these reactive flavors. There's a lot of concepts that are related. There's functional reactive programming as explained by Connell Elliott and Paul Hudak. But then people create implementations that are functional and reactive. And they call them functional reactive, but they're not the same functional reactive that Connell and Paul Hudak created. And then there's also reactive programming that touches on these things. And we have stream programming languages, and people create functional reactive libraries on top of stream programming languages, and no one really understands what they are. And then there's monadic stream programming, and you can implement all of those ideas on top. And then there's temporal logics and runtime monitoring. They're kind of all connected. Don't take those boundaries too literally, like I just did it quickly. But the point is that these things overlap, but the boundaries are not clear. So what I want to do today is kind of to bring everybody back to the original concepts and to show how you could manifest basic constructs in FRP, and also how you can do so in a library that is maintained, is actively maintained, and has been maintained for more than 20 years, and will continue, presumably, will continue to be maintained. So the key takeaways of this talk is that when you describe these systems, these time-varying systems, and we're going to use animations, but you could use it for many other things. People have used it for robotics. People have used it for epidemiology, like all kinds of things. You should focus on the meaning. And the second takeaway is that you should focus on simplicity. It's very tempting to start trying to optimize your code too early on. And if you focus on simplicity and compositionality, then you will get a lot more out of your code, and it will be easier to understand, easier to debug, test, and so on. So to get everybody up to speed on how to draw, we're going to use Gloss. It's a Haskell library for pictures. It's very, very simple to use, as just a few primitives and combinators. And the main data type in Gloss is one of a picture. So for example, you can define a black circle, which has type picture, with the primitive circle solid, and then you give the radius, and that's it. There's a function that you have to call to paint any picture, and when you call it, that's what you get. So I think everybody can kind of follow that. You can apply the color orange, the color constructor to a picture. You just have to pass a color in another picture, and then it changes the color of the picture, right? It's kind of pretty easy to use. This is not my work. This is someone else's work, just to clarify. And you can move pictures. You can use the translation to move a picture to the left. And you can put pictures together. So you can take one, move it to the left, take the other, move it to the right, put one on top of the other. put them in an array, sorry. And then with the pictures constructor, you can kind of take a list of pictures and create a new picture. So it's, again, this idea of combinators. You can, scale pictures. Here we put 4 together at different zoom levels. The scaling takes the horizontal and vertical scaling, so you can stretch something sideways or up and down. And you see that it's scaling applied to the same picture. So this down here would be a picture. And it's a pure language. One of the important things is there's no I/O going on in these definitions. There's no side effects. So you can use all the power that you have in a language like Haskell to write your expressions. Here we're using list comprehensions to go through a list of points and a list of scaling factors, and then apply a function based on those. So we're using just key functional programming concepts. You can, of course, rotate them. We'll use this a lot in our examples. And you can also draw with lines, which we probably will not use, but just to illustrate how the library works. Okay, so if you were to write an animation using this library, how would you do it, right? At its core, an animation is just a function of time. It's a function that for any time presents a picture, right? You can think of it that way. You can think of it as a function that for any real time puts a picture on the screen. In the same way that, for example, you could think of a melody as something that for any time puts a sound or plays a sound. And sorry, I know that there are experts in music here, and I'm not, and probably that's insulting someone already. But you get the gist of it. It's something that varies over time. So you could use an abstraction like this to create animations and things that vary over time. You presumably, like for example on the left, you have a definition of A, which varies over time, and then you could say that B is defined in terms of A by sampling A at the same time and then subtracting 1. And then what you would get is that the signal on the left and the signal on the right is the same as on the left, but going down by 1 unit, right? So in principle, you could do something like this. And this is what it would look like if you took the pictures that we saw before and you extended it in the same way, just taking time as an argument and using it in your code. So if you were able to draw this, it would be a circle, an orange circle that moves towards the left as time moves forward, because the translation, moves to the right as time moves forward, because it's being translated by the amount of time, right? The problem is that it doesn't quite work well if you do it that way. And the reason is that imagine, for example, that you want to write a program that is interactive. So in this abstraction, you could say that the mouse position is also a signal of time. It's something that varies over time. So you might want to draw a moving picture that is at the mouse position by saying, well, the picture at a particular time is going to be a circle positioned where the mouse position is at that time. So the mouse position also takes a time argument, and you query it, you get the coordinates, and then you position the circle. The problem is that you can do this and say, well, give me the mouse position at a time plus 3. And now how do you run it, right? Because that's the future. Or you could say, give me the mouse position a year ago. And that means you have to keep a year's worth of mouse positions. Or that number could be determined at runtime, so you don't know how much you have to keep. Maybe you didn't even look at that time. You didn't sample, you sampled right before, right after, but not exactly at that time. So how do you interpolate? So all the temporal languages and frameworks create some sort of abstraction over things that vary over time for these reasons, because they break causality, they lead to memory leaks, undefinedness, and so on. And in FRP, the main temporal abstraction is called a signal or a behavior. And conceptually, it's what you saw earlier, is a function of time, but there's additional constraints. And in the framework that we're going to use, instead of writing systems in terms of signals, we're going to use something called signal functions. And the idea behind the signal function is if we get the input signals that we're going to we have available, for example, the mouse position and so on, we can define a picture based on the input signals like the mouse position. And the constraint of these signal functions is that they have to be causal, meaning that in the output signal, the value at a time cannot depend on the input signal at a future time. They have to respect causality. And there's, again, a language of primitives and combinators that you can use to define these. So, and these languages prevent you from introducing memory leaks and so on, right? So the way that we're going to use it in this particular talk is through kind of a data flow chart system where signal functions can be connected to one another. You can pass the same input to two signal functions. You can put them in parallel. You can apply a signal function to one input and not the other, and so on. And I'll show you the syntax that we use. This is not necessarily the only way to do FRP. It's just one way to do FRP. Okay? And this is called arrows. I don't know how many people are familiar with this, but yeah, the abstraction is called arrows. So the way that it looks like in code is like this, right? You have a signal function, and instead of writing them from left to right, you write them from right to left. So this is the input of the signal function. You pass it to the signal function, you pipe it to another, and the output you call middle, for example. So this is just the way that you're calling the output of this transformation. And then you put middle here, and you apply these two in parallel, and you pass it to that one, and the output you call final. So now you're defining a signal function in terms of these blocks, and the input to the big thing is called input, and then at the end, the output that you get from all of this transformation, you apply this function transform, whatever that is, and that becomes the output of the whole thing. So you kind of have these building blocks, and then you kind of connect things across, and then you can apply signal functions, and you can also apply normal functions to these things. Does that make some sense? So now I'm going to show you how we use this to draw pictures. The implementation we are using is Yampa, which has been around for many, many years. I'm the current maintainer, but I'm not the original developer. It sees releases every 2 months, like clockwork, like we don't miss a day. And it works with all versions of the Haskell compiler from 7.6, which was released many years ago, to 9.6, which is the latest release. It has been used in industry, in commercial games, and it has been used in 2D and 3D games. So it's a fairly good implementation, but there's others available, and I'm not saying this is the only way to go by all means. So let's take a picture and try to move it around. Yes, thank you. So in this case, we just want to make a picture animated. We don't really depend on anything. We don't have any mouse position and so on. So what we have a signal function in the system already predefined that will give us the current time. And we can use it to query the time. And then we rotate a fixed circle, which is just a circle moved to the right. It's a solid circle that is red, and it's kind of moved to the right and up. And we rotate that thing. So essentially what we do is we take the circle, we displace it, and then we start rotating the whole image, right? And this is what, hang on, this is what we should see, right? So it's relatively simple to draw these things. There's an example in the Gloss library. It's a color wheel. I'm not going to go through all the details, but as you can see, you just take a number of colors, and you apply the same transformation. You put one circle here, one color, another here, and so on. And when you do that, you get this cute little picture, right? This is not mine. This was already included in the library. But then you can apply the same transformation as you saw before and say, I'm going to rotate this thing. And I'm going to rotate it by an angle proportional to the time. And in this case, instead of rotating all the time in the same direction, what I'm going to do is I'm going to apply the sine function. And when I apply the sine function, you know, the sine goes like this. So it's going to go fast in the middle and then slow down at the top, and then fast down and then slow down, and so on. So when you do that, if you play it, you get something like this. And it kind of moves and then slows down, moves and then slows down, and so on. And you're focusing on what you're trying to say. If you see the examples that I'm showing, there's no notion of sampling. There's no notion of change. There's no notion of updates. It's just the meaning of what you're trying to say. So, okay. Let me just show you one more example, and then we'll go into simulations. So the idea of this one is kind of similar to what we saw. Essentially, we take a circle, we paint it with a color, and then we move it. But the difference is that now we move it by a factor that depends on the time. So we capture the time, we apply some transformation, and then we move it right and in by that factor. And when we do that, we see this effect. Kind of opens and closes, and opens and closes, and so on. So again, very simple expressions that suddenly become very visual, right? So although this is cute, it would be pretty hard to create something like visually appealing and interesting just with those pictures. So I'm going to show you what else we can do with these frameworks. When I talk about simulation, I talk more about physics. And these frameworks also know how to do integrals and derivatives. And that also, it's just an approximation. It's not numerically accurate, but it's enough for a 3D and a 2D simulation, like a basic one, like a game and so on. And they provide these signal functions. So if you put an input signal, out comes the integral or the derivative of that signal, the approximation of the integral or derivative. So we all know from physics, the position of a falling, something that falls from the sky is the velocity is the integral of the acceleration, the position is the integral of the velocity, and that's the position, right? That's the vertical. So we could take a picture, paint it, and then translate it by that position, where the position is calculated using this signal function. And if we do that, we see this. And you will notice it kind of goes faster and faster and faster. It's a little bit slow, the animation, but at the beginning it goes very slow, and then it starts speeding up. And if you had a bigger screen, it would speed up a lot more. So you can play with these ideas and then take physics equations and just put them on paper. And I'm not going to walk you through these things, but essentially the attraction, the force of attraction between two bodies in the universe is determined by this formula, where it's directly proportional to the masses and inversely proportional to the square of the distances between them. So if you put these things, you kind of derive this equation from the textbooks, and you could just write it directly. So you can say that the magnitude of the force is the constant of gravity multiplied by the inverse of the dot product of the position with respect to the center. And then you calculate the vector, integrate, and you get the position. And when you do something like this, you get that kind of animation, where you have this at the center of the screen, and this second body gets attracted to this body, goes fast, and is orbiting the central point. And this comes directly from this code, which is just the physics equation. Again, we're focusing on the meaning. We don't have to optimize to make it executable. And as a last example, and then I'll just show you pictures. Okay. We're going to take that and create kind of like a planetary little simulation, like a toy simulation. So we do the same, but we're going to have 4 planets and the moon, and we want to know their coordinates. So we kind of pack them together in a record. And we use the same formula, except that we're also going to take into account the mass of the sun, or the main body around which the secondary one is orbiting. So we have to put it here so that the forces kind of look right. In the previous one, we kind of assumed everything had mass 1. And when you just write the equations, again, from the textbook, and you calculate the positions of the different astronomical bodies, so you say, well, Mercury starts at this position with this velocity, and it orbits around the sun, so I have to put the mass of the sun in the equations. Same thing for all the other planets. And then the moon, I put the mass of the Earth. Thank you. And when you do that, you just paint the circles in those positions, paint little circles using the library that you saw. You get this, right? Which is a kind of like cute little simulation. And I mean, it's not a scale, and it's not accurate because you know, the equations don't really work exactly that way in the universe. Like planets attract each other and so on. But it's not just that everything's orbiting around the sun and the planets are ignoring each other. But it kind of looks all right. But the funny thing is, if you replace the drawings and use OpenGL to draw, then this is what you get. And this was literally the same FRP code. All right. So now I'm just going to show you a few more things that you can do. But we're done with the code. Don't worry. If you made it this far, then you've made it already. So these are some of the other examples that you will see in the paper. And the paper is executable, so I'm happy to send it to anybody who wants. It's literate Haskell. The images in the paper are extracted from the LaTeX itself. Here, you can just combine things to turn around. And you can also create, oh, this is simple, cute little Wi-Fi kind of symbol. Again, you will recognize the sine function here, right? This is the same as the previous one, except that things are laid out in a circle, but it's exactly the same thing. And there's also an example of something that looks a little bit like clouds that are moving to the left. And these are just circles becoming bigger and smaller, but it kind of creates that effect. And just a couple more. Some of these, if they're not in the paper, send me an email and I'll send you the animation. I'm happy to share. And I'm going to show you, you can also do fractals because you can compose things because the language is inherently compositional. So if you start duplicating things and moving them left and right and start composing them, you get little animations like this. And they can get pretty interesting. So this kind of looks a little bit even random-ish, even though it's not. And this is just a small piece of code, just signal functions composed with each other. A short snippet generates an animation like this. So that's it. That's all the animations I had. There's more in the paper. The paper is filled with examples. And again, if you saw something in the video that is not in the paper, I'm happy to send it to you. My goal is to make it longer and longer and add more examples. Yampa is actively maintained. You're welcome to join the project and collaborate. There is another FRP implementation that is related. It's called Dunai. And you're also welcome to visit. And there are things that I didn't discuss, but if you focus on simplicity and if you focus on purity and if you focus on the notation, you get a lot of things for free. One of them is that you get a lot of help for testing. So you get the ability to test in ways that you cannot do in imperative languages, for example. You can also exploit time transformations, make things go faster, slower, or even go back in time. So just to recap, the FRP is a temporal abstraction. That's what it's about. It's not about change, reactivity, updates, propagation, nodes and networks. That if you focus on meaning, then you obtain reusable and compositional code. And that even though these constructions were quite simple, they end up being sophisticated pictures. And anyone can do this. This is attainable for everybody. So that's it. That's all I came to say. I'm happy to take any questions.
Amos Robinson.
Can you?
Sorry.
Thank you.
Amos Robinson from ANU. Can you talk more about the distinction of Dunai?
Yeah. So Dunai puts a monad in the. Actually, I don't want to take too long, but yeah. So. Oh, it's okay. Okay, so the implementation of a signal function is like this. It's completely pure. Given an input and the time since the last sample, it gives you the output and a continuation. So in the future, you use this one to simulate the rest of the signal function. In Dunai, you have a monad. And if the monad is identity, then you get the same. Well, if you put time, actually, this doesn't exist. But if the monad was identity, you would get the same thing, right? But if the monad, for example, is maybe, you get signal functions that terminate. Because the output may be nothing. And the continuation is nothing, so you're done. You can't simulate anymore. If the monad is either, you terminate with a result. You may be left with a result or write and continue. If the monad is list, then you can parallelize. You have multiple outputs and multiple continuations, and you decide how to follow it. You can use a reader to pass data to all the signal functions without having to pipe it manually. You can use state. So it's very, very versatile. And there's an implementation called Bear River that gives you all of Yampa's API on top of Dunai. So it's API compatible. You just go to your Cabal file, comment out Yampa, write Bear River, and it works. And yeah, that's kind of the gist of it. Thanks.
Any other questions here?
Hi, yeah, John, Columbia University. Great talk. I wanted to ask, so since Yampa is implemented essentially sort of as a library within Haskell, and it's very attractive because you get to, express just what you mean, and you can do that, right? As opposed to having to have the cognitive overhead of like thinking about an imperative language. But then you're also getting a lot of users who might be interested in making art or sound to or animation to use Haskell, and I'm wondering, in your experience, especially as a maintainer for Yampa, like what are some of the difficulties they encounter when trying to use the framework in your library?
That's a good question. I think so. Historically, in the Haskell community, there's been a little bit of resistance towards arrows. Like people didn't seem to get it at first. And I've made a lot of effort into conveying the idea that Yampa is not married to arrows. You can use applicative style and so on. I think that's been one factor. Apart from that, just lack of examples, lack of tutorials, things like that, which you are more than all welcome to contribute to, like create your own, right? I think that's been it, yeah. There's no technological limitation, nothing like that, as far as I could see.
Got it, thank you.
Mm-hmm.
All right, I think there's no questions on Discord, and I think we're out of time, but let's thank the speaker again. Great talk.
Thank you.
All right, our final talk of the first session will be Alistair Bahari from University of London. He's again remote, so the talk will be presented, recorded. It's about 20 minutes long, and so we'll have about 10 minutes for questions afterwards, so please think of good questions.
Hi, my name is Alistair. I'm going to be talking today about a functional EDSL for mathematics visualization that compiles to JavaScript. Just a little bit about me. I've been a .NET programmer for quite a long time now. Just been an F# programmer for about 5 years. I'm currently an economics student at the University of London's EMFSS program, and I'm interested in all aspects of open source mathematical computing and how software and languages are used in math education. So I'm going to talk about Sylvester. Sylvester is a functional EDSL for mathematical computing. It aims to provide a unified notation for symbolic, logical, visual aspects of mathematics, and to provide a unified functional language interface to different open source tools libraries. Probably going to be tools Maximo, Z3, GSX. So what does all that mean? What does it mean to provide a unified notation and unified functional language? Well, let's get into our first demo, so we can just look at what Sylvester is trying to do. Okay, so we can first look at some symbolic operations. Okay, so we open our Sylvester namespace, and we declare two real symbolic variables, and we're going to be using these two symbolic variables throughout our demo. Okay, so we can do things, we can express different math operations, symbolic math operations, or we can do things like algebraic expansion, simplification, partial fraction expansion, okay, trigonometric expansion, trigonometric reduction. Now, here we're defining a function of one real variable. Okay, and we can do the typical operations. We can differentiate and integrate on that particular function. Okay, now Sylvester uses maxima by default for its symbolic operations. Okay, so we can just look at the output of maxima. So as we're going through the demo, Max is going to be processing these symbolic operations. Okay, so what we're doing is we just provide a functional language interface over maxima. Okay, so basically, instead of using the maximum native language, we can use F# DSL to do symbolic operations. Okay, so let's look at some linear algebra operations. So we define a 2D vector, and all objects in Sylvester by default are fully symbolic. So as we're doing operations on linear algebra, they preserve the symbolic form. Okay, so just we're doing addition, just taking the inner product. Okay, and the same thing for a matrix. Now, matrices use number-dependent types, which lets us express the number of rows and columns in a matrix as part of the type. Okay, so we can define a 3x3 matrix here. And, well, we can do things like just simple algebraic operations on the matrix. We can do things like elementary row operations. So these operations are very, very common in linear algebra. So things like multiplying a particular row by a scalar, or switching out one row with another in a linear equation system. This would preserve the linear equation system. We can create an augmenting matrix, so we can augment that matrix by adding a vector to it, and that vector becomes one of the columns. Now we have a 3x4 matrix. Now, because Sylvester uses number-dependent types, if we look at this particular operation, this isn't conformable. So n by m isn't conformable for multiplication in this particular order. So if we try to execute this, it actually gets a type error because the two aren't conformable for multiplication. Okay, but in the other order, then this is okay. These two are conformable. Okay, so this is okay. Okay, so we can look at some, so that's the solver operations. So we can use Sylvester, Maxima has a pretty good linear equation solver, and we can use Sylvester to express a linear equation system and just solve this particular equation. So Maxima can solve this pretty easily. We can also use Z3. Z3 is an open source SMT, satisfiable modular theorems solver from Microsoft. It's really, really popular. And Sylvester provides a functional language interface to Z3. So here we're expressing a particular optimization problem. We want to maximize the area of a rectangle, given that the perimeter of the rectangle is 100. So this is how we express that in Sylvester. And we can solve this pretty easily using Z3. Okay, so here's the same optimization problem, but we've added some more constraints. Okay, we have that we set r equal 5, and we use another constraint, and Z3 can solve this pretty easily again. Okay, so note that we're using this double equal sign operator. So I'll come back to that when we look at logical operations in Sylvester. Okay, so if we look at, let's look at logical operations. So Sylvester comes with its own proof assistant called self. So we have a theory of real numbers. Now, remember I said that we were using the double equal sign operator. Now, we have the standard F# equality operator. These two expressions, they're not the same expression because they have the symbols in different form. Okay, so this is actually false. It's not true that these two are the same. But we know that in the theory of real numbers, those two expressions are actually they're actually equal because real numbers are commutative, right? So this particular expression is actually the same. So what we can do is in Sylvester, we can express, okay, that our real number theory, whether or not it says that this particular expression is equal. And in this case, it actually is. So this is true axiomatically. Okay, so if we try to just create a theorem from this expression, then yeah, this is true axiomatically. Okay, so self tells us this is true because of the theory, the axiom of commutativity. Now, self is an ML cell proof assistant, so we can't construct theorems without incompleteness. So if you look at another expression, this particular expression, now this particular expression, in order to show this is true, we actually need a proof. We can't construct the theorem like this because we don't have a proof of this. Okay, so to construct this theorem, we need to provide a proof. And this is a really simple proof. I mean, we're just applying commutative rule on the left-hand side. But once we have a proof, that's when we can construct, that's the case that we can construct a theorem. And theorems, I mean, this is a pretty simple theorem, but theorems can range from, the theories and theorems can range from the entire range of mathematical domains. I think from real analysis, linear algebra. There's no limit as to what sort of theorems you can express and prove using SILF. Okay, so we looked at the symbolic and the logical operation Sylvester. So let's look at the visualization aspect of Sylvester. That's what we're going to focus on today. Okay, so here we're going to just we just want to visualize that function that we defined before. We just want to visualize f. Okay, so this is how we visualize f, that functions in Sylvester by default. We just use it as a simple draw command, and we say we want to use the defaults. Now, if we want to use just have user specified properties, so here's how we do it in Sylvester. So when we draw it like this, basically we're specifying that we want the x-axis range to be a particular value, and we want the y-axis range to be a particular value. So this is how we just simply, so what we can do is we can customize how the visualization is rendered using parameters we pass to the draw command. Okay, and so here we're defining another function, sine function. In this case, we have a real constant called a, and we define a function in terms of that. And what we can do is we can say, okay, when we're visualizing f, that particular function, we want to set a to 1. Okay, so here's where we just set a to 1 and we visualize it. And of course, so we can just specify what value we want for that particular constant in our visualization. And the visualization will render because of the properties that we set. Okay. So here we're using a more complex set of properties. Okay, so we're going to specify the x-axis range. But what we're going to do is we're going to say we want to use an interval for that particular constant a. Okay, and if we use an interval, well, we have to specify the range of the y-axis, because once the axis is rendered, it can't change. So we need to specify by default what the range is going to be if we're going to use intervals in our visualization. And we're going to say, okay, we want to have a red plot, and we're going to increase the stroke width of the plot. So we can draw. So this is what we get when we render using those parameters. So we have a slider here, and we can use the slider basically to increase the value of that particular constant a. And this would just change it dynamically, the visualization. Okay, so this is a more complex. So, but I mean, even though it's a more complex visualization, the syntax is still relatively simple. You don't need to use JavaScript or anything like that. Just to get this sort of interactive visualization. Okay, and we can also visualize things like vectors. So here we're defining a vector, and we're going to say that we want to draw. We want to draw basically another vector. So let me render this. Okay, so what we've done is we're looking at a vector. So, and we define the constants. So the vector is a symbolic vector, and we say that we want to range the constants. We want R to be 1 to 9 and S to be 5 to 10. So we can just use our sliders again just to change the value of that vector. And of course, that happens in our visualization. So that's an example. So basically, the goal is that any object you can express in Sylvester, by default, you'll be able to visualize it using that draw command. Okay, so we looked at visualization of Sylvester. So why Sylvester? Let's now talk a little bit about what motivates developing yet another mathematical language, yet another programming language. Well, if you think about what's the role of computers in math practice and education today, you think of high school students doing homework, or college students working on a proof or for an assignment, or researchers working on a paper. And I mean, the thing was that what we use computers for, well, of course, we use it for numerical calculation. We use it for reference material lookup. We look up on Wikipedia, we look up on textbooks. For communication, I mean, talking with others, talking with our instructors, doing things like document management. But I mean, if you think about the core practice of math, what we do. Computers and software, they aren't very central. I mean, you can basically do math completely without using computers and software. That's how, I mean, that's if you're growing up, that's how a lot of us actually did math without having to use computers. Okay, today students use computers as devices for numeric computing or for things like communication and reference lookup. And the numeric capabilities of computers are very accessible. Okay, that will be able to calculate numbers is very accessible. But those other capabilities, like the symbolic, logical visualization capabilities, they're not really that accessible to end users. Okay, and I think that's one of the reasons why, even though computers and software, they've altered the core process of things like business. So today, things like accounting, stock keeping, you wouldn't think that you could run a business or do business today, without really like using computers, running a large business anyway. But that's not really true with mathematical education. I mean, today, even though of course there are a lot of differences, but I mean, fundamentally, other things that we do are still the same as we did, centuries ago. Okay, so computers really haven't altered the core process of math education and practice. So, what's the reason for asbestos? So basically, the question is, can we make computers and software become fundamental to math practice and education? Okay, and so right now today, for the software for higher mathematics, we have computer algebra systems and we have theorem provers, and it's kind of split between these two generally categories of software. So what Sylvester tries to do is it tries to give you a syntax for expressing these different aspects of mathematics, a single language, a single interface for doing all these things. So basically, so you can have a single language and a single environment like Jupyter notebooks, where if you're solving university level math problems, you can have a single language to be able to do that. And of course, as the language develops, to be able to go beyond that, if you're doing research, that's sort of the broad view of Sylvester. Have a single language and a single interface for doing higher mathematics, and to try to make computers and software really central to the whole math practice and education today. Okay, so we can focus. Let's just focus on the visualization aspect of Sylvester. So Sylvester, we saw that there's a high-level API around that draw command where you can just draw mathematical objects and you can set parameters using that particular syntax. Now, there's also a low-level API, and this is a functional interface to GSX graph, where you work with objects. Instead of looking with mathematical objects, you look at objects like points, lines, polygons, all the different elements of interactive visualizations. Okay, so GSX graph, it's a cross-browser JavaScript library for interactive geometry. Okay, so that's really, so all the visualization that we saw before, they were rendered using GSX graph. Okay, now GSX graph is really designed it was really designed to be embedded in web applications or, applications like Moodle, and the target audience was really web developers. So what's about us? It provides a functional language interface to GSX graph. So that's the low-level visualization API. And from that low-level API, what you can do is you can build higher-level visualization functions. So we can just look at the low-level visualization API. So I'm just going to switch to out of presentation view for, but just so we can look at the code and see how. So this is an example of using the low-level visualization API. So this is we're just defining another function, and we're going to be using so these are all GSX graph objects. We have boards, we have sliders, function graph. This is a Riemann sum. So if we run this, and you can see it's all basically F# code. Okay, so what happens is that when we define this code, we define it inside the F# quotation. And defining this in an F# quotation, it signals to the Jupyter kernel that this F# code should be compiled to JavaScript. So when we run this particular code, this code gets automatically compiled into JavaScript. So this particular code gives us this visualization. Okay, so this is just a Riemann sum visualization. Okay, and we're using sliders again just to define different parameters, the endpoints and how many strips we're using in our integration. Okay, so here's another example of using the GSX graph interface. In this case, we're actually doing 3D. So this is a 3D line. So GSX graph has 3D capabilities as well. So we can also visualize things like 3D vectors. Okay, so again, we're just using the functional language interface just to define a simple 3D visualization. Okay, so this is a more complex visualization. This is a Euler circle, but again, it's the same thing. We're using just F# code. And again, the F# code, compared to JavaScript, the F# code, I mean, it has a very, very minimal syntax. We're using mostly plain English. There aren't a lot of really like, semicolons and that sort of thing. So it's in some ways, the F# code is a lot simpler to understand than the equivalent JavaScript code. Okay, so if I run this, so this is just a basic Euler circle, and of course, inside of this, it is also interactive. You can manipulate the points. So that's how basically you can use sort of like the low-level visualization API of Sylvester to create. So we can. One of the functions I want to focus on was how do we create this visualization. So we're going to look at creating this particular visualization. Okay, so this is a visualization of an economic function. Okay, so we saw how we visualized functions before. So in this case, what we would like to do is we would like to use a low-level API. When we have more, if we have custom visualizations, or we want to really to be able to control at a low level of the visualizations, we can switch to the low-level API. So we're just briefly going through it. We're defining a grid as to this is what our graph is going to be. We're defining an x-axis, y-axis, just the labels, and we're defining how things like the stroke width. So we're setting those properties for that particular our grid properties on the board, and then we're defining our sliders. We define what the slider name is, what the range is, where they're going to be on the board, and so then we define our functions in terms of the sliders from the value. So as we change the sliders in this value, of plot chain of visualization changes. Okay, and again, we're using this just typical functional language interface. So again, in many ways it's a lot easier to define these things rather compared to JavaScript. So once we have all the elements we require, we just render that to the board, and this is the output that we get. And all of this is done inside Sylvester. We don't have to switch to JavaScript to be able to do this. Now, given that we've done this in our low-level API, we can define a high-level API. So we can define a high-level type called, let's say, market equilibrium, and just using those elements. And what we could do is we could say, okay, if I want to be able to draw this, I can just use that low-level code we just had to implement the draw member. Okay, so this is how we would implement it. And once I've done that, basically, I can use draw, that same draw command, to be able to just draw simply market equilibrium, to be able to create visualizations like this using user-supplied parameters. Okay, so this is an example how we can use the low-level API to compose a higher-level visualization API that users can access pretty easily without having to really understand the low-level visualization API. Okay, so and if we're talking about comparing Sylvester to other visualization languages, so of course there are a lot of different visualization languages, but if we compare Sylvester to that's one of the things that really it strikes. Well, so some of the things we consider is like, okay, how easy is the code to understand? How easy is it to grasp, especially by new users? Things like, static types. I mean, these things that they help users avoid mistakes. But the key thing is the reusability and composability. Can users easily create like high-level types interfaces from lower-level types or functions and procedures? That's something that I think is really, really missing from most visualization languages and libraries today. And of course, can be used interactively. Like, so certain languages like Metapost, you can't really use it interactively. They're not really for creating interactive visualizations. Okay, so and so this is just like some JSX JavaScript code, and I mean it follows the Sylvester visualization API. It's very, very close, but you can say that it might be easier. The Sylvester might be easier for a new user to understand compared to the JavaScript, because JavaScript was created for developers. Okay, for web developers, was already created for interactive use. And of course, Metapost is a really powerful visualization language for creating typeset static documents, but it's not really designed for interactive use. And Mathematica is a very, really popular commercial computer algebra system. And so you can see mathematical, it's not very long to, it doesn't take very long to create a visualization like what we saw. But in terms of composability and reusability, obviously I think Sylvester has a lot of, it's really advanced. Like there's no real way there aren't really advanced scenarios to create like compose higher level interface or some mathematical code. So that's one of the areas where Sylvester is a lot better than, say, Mathematica in terms of visualization. Okay, so that's basically a demo of Sylvester. For more information, you can check out the project on GitHub, or you can get me on Twitter at Alistair Bihari. So thank you very much.
All right. Do we have Alistair on Zoom here? Wonderful. Thanks very much for joining us. Any questions? I have maybe one to start out. I think wonderful demo, and I especially enjoyed your grand vision of connecting together theorem provers and computational software. Oh, did we lose Alistair? Is he still?
No, I'm here.
Okay, you're still here. Okay, we just can't see you.
Okay.
So I've been thinking about this myself. We have a wonderful dependently typed language, Lean, now, which has a very rich mathematical library. And I was thinking, well, maybe if we put in like 2 years of effort, we could rewrite the Python layer of Sage Math into Lean, and then we would get to the computational thing as well. Maybe not so much visualization yet. But I'm wondering what you think of doing something like this, or what Sylvester would have as an advantage over that approach.
Well, one of the things with Sylvester is that it's embedded into F#. Now, Lean, the thing with theorem prover is like Isabel and Lean, the languages are like really sophisticated. I mean, like things like dependent types. But I mean, if you talk about like if you want something that people are going to be using, like in terms of like things like tool support, like F# has really good support for like running like things like Jupyter notebooks. And I mean, one of the things is that if you have to choose between something like a really sophisticated language like Lean versus like really broad like tool support, like community support, I think that the broadly supported language would win out eventually. And that's why I think that having a embedded DSL in like a mainstream functional language, I think it has a lot of important advantages over using something like Lean. As sophisticated and powerful as Lean is. I think that just in terms of the size of the community, the tool support, I think it's always going to lose out to like a more mainstream functional language.
All right. Yeah. Thanks very much. I mean, I think definitely I'd love to see this vision come to life. Right. This is very valuable for everybody. All right. Other questions here?
So I just have a question about your, I guess your design decision, also kind of, the design decision about using kind of like an F# embedding versus just, you're kind of touting that as a benefit over JavaScript. But I was kind of curious if you did, if you had any studies or anything to kind of support that, that design decision, that it would be better to use a different language other than JavaScript to create these JavaScript visualizations.
Yeah, it's more like a rationalization because JavaScript is basically, it was tagged originally for web developers. It inherits a lot of the syntax from C and C++. It wasn't really designed to be used like how we saw we were doing it like in a Jupyter notebook. JavaScript wasn't really designed for it. So no, I haven't looked at any like empirical studies about like the usability of JavaScript compared to the F#. But I mean, just in terms of like, if you just look at the way that like functional languages, just in terms of like the syntax, and I mean, I think that for like, if you're, let's say like you're like a teacher or like a student and you're like new to programming, I think that the syntax of like a functional language that tends to like leave out like stuff like semicolons and braces and all the stuff that C family languages have. I think it looks like less intimidating. So I mean, you know, it's I mean, so yeah, but yeah, but that's a good one actually. I mean, I really should like try to get some like empirical data, like you know, what people really prefer, what they find useful, you know, compared from like JavaScript compared to like functional languages.
Great, thank you.
Hi, I have a couple questions just about functionality. I'm curious if there are ways to tie multiple variables to a single slider or to create a cell whose image is time varying and not slider varying.
Well, as far as like time variant, well, if once you start thinking about things like animation and time variables, then you're looking like a more advanced. Then you have to go not necessarily to JavaScript, but you have to basically write code that like talk to JSX graph at like a really low level. So yeah, I believe it is possible to do because I've seen demos of JSX graph with like animation and stuff. But yeah, that's like a really advanced scenario. And well, I mean, so it definitely is possible, but probably what you would want to do is if you were to implement like a component like that, you would try to like want to have like a high level API that someone could just basically just plug in, like it's like a you know, just like so if you set like a property, and that would basically like automatically fill out like the different variables. So you know, one of the things that like using F sharp that's basically so you can just have like a high level API and not have to worry about dropping into like those blocks. But yeah, I believe it is possible to do what you're talking about. Yeah.
Thank you. Are there any more questions or are there any questions on Discord? Well, we still have another minute, so let's give it a few seconds for people to think. But I'll just take this moment actually to do a quick administrative note. We accidentally captured all of your images on the live stream while we were switching the cameras so that Alistair could see us. We will have to edit this to get rid of that because we don't have your recording release. But if this is a sufficient problem that we should take the stream down now, please see me in the break. We can absolutely do this. I'll need your proactive effort to tell me about this. Otherwise, we'll leave it up and edit it later. Any last questions? Well, thank you again, Alistair.
Okay, thanks very much for having me. It's great.
All right, I believe we now have a break until the next session of this morning. Farm only has 2 morning sessions. The afternoon is free, but the performance evening is essential. That'll start at 7:30, about, a stone's throw away from the building. Information's available on the website and on your printed programs. Also, I haven't met like most of you because they don't usually come to Farm, and I'm excited to. So hopefully I can see you all during the break.
Testing? 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 1, 2, 3. What do people say?
Struggling.
Are we talking about the resolution of the projector? What is the thing we are currently trying to fix?
Oh, I don't know. It just looked really blurry. Although this is looking better, I think.
The blurriness is not blurriness. It's just that the resolution of the projector is terrible.
No. Thank you for taking care of it.
Hey everyone, we're a little bit past the hour, so it's about time for us to start. Thank you all for coming to the second session of FARM. This session's special feature does not compete with the Haskell keynote. We've got Amy from, yes, thank you all for coming. We've got Amy here from the University of Washington to talk about knitting programs with twine. Before we start, I just want to take a plug, as I always do, that this evening we have a performance with an exciting keynote by Gloria and so many cool things starting at 7:30. So please arrange your dinners accordingly. All right, take it away, Amy.
Yes, you won't want to miss the keynote. Am I too loud or is it okay? Okay, great. I'm super excited to be here at FARM. Just really excited to be talking about what we're doing because I feel like it's a really amazing community. And I'm presenting our work on exploring self-embedded knitting programs with twine. Of course, we are all at the Paul G. Allen School of Computer Science and Engineering here at the University of Washington. And so what I want to talk to you about today is how I want to design new and better computational design tools for knitting. And knitting, why would I care? It's because knitting is super important to our everyday lives. Take a second to ask yourself, how many knit objects am I wearing today? How many of you believe that you're not wearing any knit objects at all? I would take a second to bet that probably all of you are wearing something knitted. Probably most people in Seattle are wearing something knitted. And so knitting is super ubiquitous in our lives. And knitting is also a really exciting computational fabrication research field. And so far, there have been many systems that have been published, and they're all focusing on sort of what is possible, pushing the boundaries on considerations of what kinds of objects can be created and for what costs they can be created. But today, I'd like to propose a third, completely new, radical axis that nobody has even thought about exploring. replication, replicability. That is, whether a knit object has the ability to replicate itself. And this is not in the asexual reproduction kind of way. But when I say that, I mean, when I say new, better representation, I want a knit object to be able to encode its own replication information, to encode its own fabrication plan. And like, why would we even care about this? It's because, when we encounter objects, we often want to remix, duplicate, customize, edit, and repair them, and more. So have you ever seen like a table that you liked, but you wanted to be able to lengthen it with unfolding leaves? Or maybe you had a dining set that was missing a chair that you wanted to make a fourth chair. Or maybe you had a pair of gloves that didn't fit just quite right and you wanted to make them a little bit wider. Or maybe you had a pair of sweaters that you really liked the body of one and the neckline of the other. And I chose this example, it doesn't really look good, but whatever. And luckily, this isn't too crazy of an idea because actually, objects already contain aspects of their fabrication plans embedded within them. So let's illustrate this point. Look at these two socks. What can you tell me about how they were made? Maybe you could start by asking yourself what material they're made of. Are they made of the same material? And probably, exactly, you could have guessed they're made of two different materials. Maybe you could say, the one on the left is made of wool, and the one on the right is made of like nylon or something. And if you have, a certain amount of expertise, you might be able to say even more about those fabrication plans. Like you could say, okay, the sock on the left is like stranded knit, it's knit in the round, it has like a fish lips kiss heel, and so on and so forth. And the one on the right is like warp knit, it has like a denier of 20, blah, blah, blah. And so the more, expertise that you have, the more you can say about the fabrication plan. But there may be many reasons why these aspects aren't actually enough. To recreate the full fabrication plan. For example, there could be many ways to achieve certain types of effects. The process of learning the full plan might require a lot of iteration, making and testing, or even destroying the original object. And so the question is, how do we make it so that the whole plan is recoverable without going to such lengths? And to provide enough information for these tasks, we kind of want to explicitly encode fabrication plans into objects, effectively making them open source. Anyone can take them, remix them, customize them, edit them, or whatnot. And so when I first started thinking about this problem, there's a couple obvious things we could try. We could try adding a QR code to it so that when you scan the QR code, it goes online and you can download the plan. But is that really the object carrying its own fabrication plan? This is relying on the infrastructure of the internet and everything that supports the World Wide Web. And another idea that we had is we could just draw the fabrication plan onto the object. So here's like an origami table. I just put the fabrication plan on it. So that definitely works. But I think we're not taking advantage of this really interesting perspective that applies to knitting, which is that in knitting, you can often trace the input, like the knit instruction, directly to the output of the instruction. So here you've got this knit instruction. It is producing this knit stitch. And so in a way, the final knitted object is kind of encoding a programmatic structure within it. So with this perspective, we can imagine like the behavior of these self-embedded objects is kind of like this. Like you start with a knit object, and then you compile it or you execute it to self-replicate, and then you get another knit object, and then you can compile or execute it to get another knit object, and so on and so forth. And you could produce like infinite sweaters. And that kind of sounds a lot like Equine. We're basically trying to write Equine for fabrication. And to recap, Equine is a program whose source code, when executed, produces itself. And what we're trying to do is write a fabrication quine, like a quine that compiles to a knit object. But that kind of means that the input should also be a knit object. And so there's this obvious difficulty here where I don't know of any compilers that can take knit objects as input, like a physical knit object. There's no machine that you like scan in like a sweater and then you get another sweater. And so we really need some way to like decode the original fabrication program from the knitted object. So really the question is, can we design a language that allows us to easily encode and decode fabrication quines from these knits? And a little more formally, we want to be able to write these two functions, encode and decode, over the representation. And when it's all said and done, your input program, once encoded and decoded, should be equivalent to the original program. Great, so we kind of have an idea of what we want to do, and we have some formal criteria for the representation. But I'm going to talk about other stuff in the talk too. But first, I'm going to point out that doesn't really paint the full picture. The design space of self-embedded objects is really large, and there's many valid points in the design space. So we'd like a framework for evaluating various points. And to that end, we propose some like desiderata and some considerations that all solutions should be evaluated against. So here's an overview of the 5 different points that we identified. We have decodability, expressivity, compression, robustness, and locality. Some of these might trade off of each other. So if you're a designer, you might sacrifice some of them in order to pursue others. And let's take a look at them in a little bit more detail. So the first and probably most important one is decodability. We want to make it explicit and easy to decode the fabrication plan from the object. Definitely easier than using your expert knowledge to reconstruct the plan like piece by piece. And so what we propose in our work is using the color channel for knitting. And there's 2 reasons for that. One is that we already know how to knit colored objects. This sweater is an example of something that uses many different colors. Color is also very visually salient, so it's easy to see like what the color of a single stitch is compared to here on the right. I have a picture of like texture being varied, and it's a lot harder to see texture information for a single stitch. Our second criteria is expressivity. So let's say, for these couple slides that we've got some red markings with drawings with red markings on them. Let's say that those denote the visual encoding of our fabrication plan. And so really expressivity is all about allowing people to make the things they actually want. We want a wide variety of knit objects to be expressible, and we don't want to necessitate certain designs. So like if we have a world where when you see a red instruction, that means knit a 10 by 20 inch rectangle. That's great for the world where we only want to knit 10 by 20 inch rectangles. But you can imagine people probably want to knit other stuff too, like sweaters. Our third example, criteria is compression. And so similar to how decodability avoids the difficulty and ambiguity of like this tedious expert reconstruction, we want compression in order to avoid something like reconstructing the program by decoding the stitch at a time, like every stitch individually. So that's very error prone and tedious. But that also leads into this other problem where super compressed languages might be less robust. And we really don't want to lose all of our fabrication program just because like a certain small part of the object was destroyed. And then finally, our last criteria, which is a little bit aesthetic, is that we like this idea of locality, which is that the instruction is very close to the output of that instruction. So here you can see like maybe we've got the instructions for the sleeve on the sleeve, or we've got the instructions for the body on the body of the sweater. And you can take that to, it's like a sliding scale, you can take it to a farther end, and then you get more of a distributed expression of the fabrication plan, but you could like run into compression issues and so on. And so those are our 5 criteria. We know a little bit about what our language should have, but we don't know what the language is going to look like. And that's because I haven't told you anything about knitting yet. Because in order to design a language for knitting, we probably want to understand what knitting is exactly. So we're going to talk a little bit about the physical structure of the knitting, which is necessary if you're going to try to extract the code from the physical object. So I said that we were going to take advantage of the programmatic structure of knitting to embed programs within it. But like, what is the structure of knitting? The basic building block of knitted items is loops. And what it really is loops pulled through loops, interconnected loops on a continuous yarn. So if I just took this like set of loops and I just pulled it at the end, I'd get just a straight line. So that would lose all of its structure. But what you really want is to have loops pulled through loops. So here you can see we've got a series of loops that have been pulled through other loops. Now if I grab the ends of the middle loop, it's like stays in place. It's totally fine. It doesn't move because the head of the bottom loop and the tail of the top loop are holding it in place. So the way that these knitted objects, this knitted structure is built up, so we start with like a series of loops, and then we go back and we pull loops through them. And then we turn around and go the other way and pull loops through those. Okay, so that's probably all you need to know about the structure of knitting. And we know a little bit about what knitting is, but how are knitted objects actually made? It's like, I said I was going to make a knitting program, but what am I actually programming? And the answer in our case is, you can make knit objects with a variety of methods. We use industrial knitting machines. So I'm going to introduce 3 important concepts of a knitting machine that you're going to need to understand fabrication programs for knitted objects. And so basically, how a knitting machine works is that there are a series of these things called needles, and each needle holds one loop. And the needles are like side by side on what is called a needle bed. So there might be like 200 needles side by side on a needle bed. So you can see in this example, like all of these are on one bed. And each needle can pull a loop through the loop that it's already holding. So it's able to make that loop-through-loop structure. Then we have these things called carriers. So that's the second important concept. And carriers, it's like that little triangle here, they dispense yarn. and each carrier can hold like a different yarn. So you can have as many yarn colors as you do carriers on your machine. And then the last thing, which isn't pictured, is this thing called a carriage, which moves back and forth across the needle bed. And so you might be wondering, like, how do the needles actually move up and down? Like, what actuates them? And the answer is the carriage, which is moving back and forth, is like pushing the needles up and helping them to retract, and that's causing the needles to actually knit. So I have a really short video of this all in action. Let's see if I can play it. So we start by seeing, yarns are hooked up, and then they're going through the carriers. We have 2 carriers there engaged. Now we can see the needle bed, and this is the top of the carriage. The carriage is going to start moving that way, and then the carriers are going to follow, and the needles are going to come out. The carrier is going to lay yarn. So there we go. You've seen a knitting machine in action. OK. So I think I don't want to play that again. So I talked a little bit about, we talked about the background for knitting. We're ready to talk about a prototype for a self-embedding language for knitting, which we tongue-in-cheek named Twine. So remember how I said we wanted to use the color channel to represent these programs? Let's take a step and think, what is the simplest set of instructions that I can use to create knit shapes? Then we're going to represent those simple instructions with colors. So knowing what I just told you about knitting, maybe you could take a second to think to yourself, what set of instructions would you use to represent the knit object that I have here? Here are the instructions that I chose. Basically, what you do is you got set direction left to right, which says start here and start knitting left to right. You've got switch direction, which changes the direction. And then you've got some machinery for basically saying knit n stitches, where n is some parameter that is specified in base 4. And chose base 4 because there's 10 carriers on our machine, so I don't want to use them all just to represent numbers. And so this is a really, really straightforward way to specify what we're going to do. And then you can see we've got these color assignments. So if I see a pink stitch, I'm going to know I'm going to set the direction from left to right. If I see a green stitch, I know I'm going to switch directions, and so on and so forth. And in fact, the specification for these really basic front-end instructions is given in an IR that encodes the machine state and the knitting program that's being built up. So let's just take a look at what a simple 36-stitch rectangle would look like in this setup. So we start here at the top with the pink. We start reading left to right. And then the next stitch over is like that teal color, so that's 3. And then we got 1, and then we got 0, and then we got repeat. So 3, 1, 0 in base. Quick! What is that in base 4? What is that? Does anyone know? It's 36. I just told you. So we're going to knit 36 stitches, and then you got repeat. And so repeat's like, OK, I'm going to knit the end stitches. And so now we continue going on our left to right journey, and then we hit the switch direction, which says go back in the other direction. You hop down, and you start reading this way. You got 3, 1, 0, repeat again. And then I have animations for this. I forgot. And then you go back in that direction again. And so great. This is gonna help us knit a 36 stitch wide rectangle. But you might notice a problem. Like 10 imaginary points to anyone who notices a problem. It's that we aren't actually reproducing the color instructions with this semantics. It's just going to make a square that is like a single color. We need to actually get those color instructions back in. So we're going to make a sneaky change to the semantics, a really simple change that will try to encode this self-replicating behavior. And that is, we're just going to, whenever you see a color instruction, also knit a stitch of that color. So now, when we see the pink instruction, we're going to say, OK, we're going to set direction left to right and knit a pink stitch. When we see switch direction, we're going to switch direction and knit a green stitch, and so on. And so here's our updated version of the rectangle. You might notice it looks almost exactly the same. But there's one important difference, which is that these numbers that I told you earlier, they were like 3, 1, 0. Now they're shorter because we still want to have a 36 stitch wide rectangle, but those color instructions are contributing to the width. So we only have 30 stitches in between the instructions on the top and 31 in the bottom, and so on. And so we've designed a language that, in theory, will create some knitted quines. Do they actually work? You've probably been seeing some foreshadowing. You've probably been seeing that the whole talk. So we started by knitting basically the rectangle example that I was showing, where here the edge colors represent the original program. So you can kind of see like how I didn't have the foresight to like get the right colors. But you can see the sort of structure of the knits resembles the original program. And you might notice there's also this really long, header with like colors of rows of different colors, and that's basically serving two purposes. One is a fabrication purpose in that it sort of helps the thing knit nicely, but the second is that it actually serves as a legend for decoding. So if you start here, this is the first one, this first color, so yellow. That means that's set direction left to right, and then the second one's red, so that means switch direction, and so on and so forth. So if you wanted to decode it, you'd start here at the yellow, and then you'd say, okay, I know that one's set direction left to right, and so on. So you can start decoding it. So we think it's successful, and we think it's probably the very first example of a knitted quine, although we invite people to challenge us on that. And so what's great about this technology is extensible to many kinds of shaping using short rows. And so what's a short row? It's self-explanatory. You start with your long rows, which are just the full width, and then those pink rows you can see are not the full width. And so that is allowing us to create shaping and knitting. And so what's great is that you can easily say, in our technology, you could easily say how many stitches are in each row, so it's really easy to specify short rows. And so I used twine to generate this conically shaped object, and you can see the short rows here through the changing of where the color instructions are. So that's it for examples. But I thought we'd talk a little bit about how this evaluates under the criteria that we set out at the beginning. And so we think that in terms of expressivity, we actually have access to whatever you can express using knitted short rows. And that's a surprising amount. If you're clever, you can make short rows into lots of different stuff. You got hats, mittens, sweaters, these crescent-shaped shawls, and other types of shaping too. So short rows are very expressible, and we leverage that sort of expressivity in short rows to create a diverse landscape of things. In terms of the other three criteria that we talked about, we think that it's not the most compact representation. It's got a decent amount of robustness because you've distributed the instructions throughout the knit object, and it's got a really nice locality because each course is encoding the fabrication instructions for that course. And I think there's sort of other interesting implications here too. For example, the sort of regularity that twine programs have give each twine object kind of a unique look to it. And it kind of makes it identifiable as sort of a self-replicating object, if you're in the know. And there's another interesting implication, which is that we're really rayifying the fabrication plan here and making it visible. And by doing that, the embedding is kind of reminding you that as much as mass-produced objects and mass availability of items might make it seem otherwise, each of these objects had to be painstakingly crafted and manufactured, and it takes a lot of energy to make that item. And so these things didn't just spontaneously appear. And I think it's easy to forget that there's a huge effort in manufacturing, but visible fabrication plans makes the making of explicit and kind of reminds us of that every time that we're using the object. So maybe it will encourage us to slow down and think about the fabrication, how these objects came to be. And so there's still some future work, I would say. There's, for example, there's kind of unsolved fabrication challenges. So I made this hat, which I am delighted to wear. And I tried making it with twine, but the drape of the fabric, I used a certain color work technique that caused a really stiff drape. And so that ended up making it sort of not so hat-like. And so clearly we still need to make advances in sort of fabrication technology that will support the creation of self-replicating objects. Another thing is that we deliberately did not handle things like decreases because we thought that it was pretty difficult to decode what a decrease looks like. You can see in this bottom one, here you can see there are two purple stitches, right? But in this bottom one, it's really hard to see what that bottom stitch looks like. So we thought it was difficult to decode in our current scheme. So we haven't supported that yet. And what that means is that we're still looking forward to what kinds of solutions will be able to handle things like complex texture and sort of shaping that relies on these types of decreases. Also, I'm really excited to see what kinds of solution we'll be able to handle different color work, because obviously since we're using the color work channel, we're not really, future work will have to handle things like beautiful color work designs like on these mittens. And I've already heard a lot of interesting ideas from people like, what if you put all of the instructions in certain locations that are unobtrusive, or what if you do it on the inside instead of the outside? And so I think there's a great potential for future work to expand on this expressivity problem. And so to recap, we motivate the idea of open source objects which carry their own fabrication plan, and we view them as self-embedded programs that are similar to quines. we characterize what these representations might look like for knitting and provide a framework for analyzing solutions in that space. We create a language with the self-embedding property and knit perhaps the very first knitted quine. And all of this is not to say that like we have solved the problem of knitting quines, but really to invite discussion and ideation and like motivate the problem and provide a framework for analyzing it, because we think it's a really interesting and important problem, and we wonder what would need to happen for the idea of open source objects to become a reality. Thank you.
Any questions in the room? Lots of questions in the room. Good.
Hi, that was really great. Thank you. One important part of the quine is being able to take it as input for real. And in your case, I feel like you manually retranscribe the knitting into instruction.
Mm-hmm.
I guess you would need computer vision to do things like what you really want. Have you tried to evaluate if your solution is, I would say, readable enough from a computer vision perspective?
So that's a great question. I haven't, so you're exactly right in that, if you want it to be fully automated, where the input is a knitted object and the output is a knitted object, your compiler would have to include like a computer vision part. Well, I think your compiler would have to include a computer vision part that would read the program out, would read, the knitted object and then like knit the object. I personally haven't looked into like whether or not this would be easy enough to read. My opinion is that if you choose like 10 different colors that are very easy for like a computer to distinguish between, then I think it should be like fairly, like I think it should be possible for certain types of objects. Obviously, like if the object's not totally planar, then you have some trickiness in that. And so I think this is definitely future work, an open question, lots of interesting questions to be had. And if you look at related work for this, they have like a lot of interesting other strategies. Like I've seen, invisible QR codes that are visible like via infrared technology and so on. So you could imagine other types of solutions to vision that could like automatically complete the loop. We haven't gotten there yet, but that's a great point.
So you focus on machine knitting, in which you have basically one stitch. Have you considered hand knitting with knit, purl, and like, or even crochet stitches in which you have a bunch of? Like, how will you encode that?
That's a great question. So I think you would probably just design your own language from scratch to support those kinds of things, because what I've been focusing on is well, I guess what the exact representation that I have isn't super machine knitting focused, but you could imagine like if you get into more complex stuff, then you would need different compilers for different backends and so on. I would love the idea of like doing it for crochet, because I think there could be so many interesting. Crochet is like so open-ended that there could be a lot of interesting questions on how to actually read the programs out. So yeah, I think that's super, super important to recognize. Very good question. Yeah.
Hi, man.
Hey.
Great stuff. So I didn't get good sense of how rigid this encoding is. So what if I love the design of the sweater, but I don't love the encoding that gives it color? So is there any like wiggle room to do it differently while keeping the essential parts?
That's a great question. I think no, not right now. I think you kind of rely on the design of what it is, like the design that you have. I think that it'd be interesting to see like what kinds of things would be possible to like make it an invisible encoding or like a less rigid encoding. So for example, maybe you have instructions that say like knit a sleeve that is like of certain dimensions, and I don't care how you do it or exactly how. So I could imagine like taking it back and making it like sort of less rigid, or as I said, you could put it on the inside, or you could do all these other kinds of tricks to make it sort of less physically visible. So I think that is like a really interesting area for future work. I really like that question. Yeah.
Hi, so I was curious, since your so most of your instructions are kind of row-based, like you have like each row starts with its encoding, but I was wondering, since you already have this kind of notion of repetition, if you could have a two-dimensional repeat as well, which might help in reducing the number of instructions in a knitted object. I was wondering if that had been considered in your design.
Yeah, that's a great question. I think you totally could. And like, in fact, you could probably create patches of like varying granularity and instructions to be repeated. And then I think you're getting pretty close to like what other computational, what real computational design tools for knitting do in terms of like geometry and patches and so on. And so I kind of wonder, your question is making me wonder if you could design sort of a hybrid where you have like that kind of geometry structure and then you induce like the replication on top of it. So yeah, that's an interesting question. I haven't looked into it. I thought about it, but we didn't implement it. So yeah, great question.
Thank you.
Thank you. That was great fun. In response, perhaps to following up on Familiar's question, how about not having the coding so blatant at the edges, but using some steganography to hide it in the texture? If you've got sufficiently different colors, then sufficiently distinguishable colors, then maybe you've got quite a lot of freedom in how you can hide pixel colors.
Yeah. Yes, yeah, the pictures of QR codes, that's exactly what I was thinking.
Yes.
Yeah. Yeah, that's a great question. I love, I enjoyed presenting because people always have super interesting ideas for like what could be possible. And I think that's especially a great idea if you could get like a computer vision system, especially because you could have these really complex, subtle encoding schemes. So I love that idea. I'm gonna write it down. Thank you.
So we're just gonna keep setting up the next person. I'm wondering if the video chair can come and lend assistance. Do we have a video chair? We do. Awesome. While we're working on this, John, where'd you go? They're having trouble getting the signal. Well, Amy, while we're working on this, I do actually have one question. The color encoding actually reminds me of the existing machine code for some looms, which is just a bitmap file with a lot of differently colored pixels. Looms for weaving, which, as far as I know, is just a bitmap file with differently encoded pixels. In that sense, if you decided to use that color information in your weave, you might also already have a quine. Does that make sense, or am I missing something important about how that works?
That's a great point, May. Actually, we talked about this when we were first like talking about this knitting thing, which is that you probably could just design like a punch card for a loom on a loom. Like you could make the punch card for the loom on the loom itself. It's like, I think that is a very interesting question. I think it could be easily extensible to that. So yeah, you're totally on the mark.
Awesome. Yeah, we're still having tech issues, so let's go.
To bounce back on Eli, a question. There is an ESO-long called Piet, which basically encode programs into pictures. And some people have tried to compress programs like that and do the kind of code transformation with quotes to try to move around the instruction and represent programs in various weird way. And I feel like there are lots of similarities. So, yeah, it's yes.
That's a great idea. Thank you.
Hey, Amy, great talk. My question is, what was the problem with the decreases? Is it that two of the same color?
So thanks, everyone. Sorry for the quick technical delay. Through a collaboration, we've got the slides up, and Charlotte's ready to start.
Yay. Yep, so today I'm going to be telling you about homotopy type theory for sewn quilts, which is a work kind of building off of my master's thesis, which I completed last year at Worcester Polytechnic Institute, advised by Rose Brower. So we have to give quite a little bit of background before we can get into the actual language itself. But first, we're going to start off by talking about quilts. So quilts are really complicated structures, and they have a huge variety of forms that they can take. Many quilters today use computers in their design process, but there's a huge range of outcomes. So if we look at our pictures here, these are all quilts, right? From different time periods. We have one contemporary quilt by Karen Eckmeyer, where you've got like this very interesting like city design. We have an Amish quilt from 1885, which is a very geometric design that might be more similar to what you associate with what a quilt looks like. And then we also have another quilt from 1885 by Harriet Powers called the Bible quilt, which is still kind of a patch-based design, but has a very different look and structure than the Amish quilt. Our goal here with this work is to be able to represent all of these quilts equally as like kind of first-class quilts in our design tool, because currently they're not. You're kind of limited in what you can and can't represent in existing tools that use patches and kind of they rigidly stick you to a grid-based design. We're kind of getting around that by taking a topological approach, because that's going to allow us to have a lot more flexibility in terms of what we can represent, because we're not really worried about the exact geometry of what we're dealing with. So why are we interested in quilts specifically? Because mathematically it's kind of hard. You think about solving geometry problems, and that's really hard math to do. And this might actually, on the other side of things, be an actual practical application of homotopy type theory, which I believe we are still looking for askers about. I think we're still looking for a use for it. So maybe this might be one. And then culturally speaking, when we're working in STEM and computer science specifically, the choice of what we're putting our time into kind of says something about who belongs here. And I think this kind of goes for a lot of the works being presented at Farm. It's that we're really trying to bring kind of traditionally feminine, traditionally like older, like quilting, it's all older women. That's just what it is. There's been studies about this. And we want to show that this is still a viable thing that computational people can look at and learn from. So how are we going to incorporate these homotopy type theory ideas with quilts? Our research question that we're kind of focused on is how we can represent the topological structure of a quilt in a programming language. And the way this kind of works out is that the program state is kind of the quilt in progress that you're constructing. So as you sew new pieces onto itself. The statements of the programs are the sewing operations that you're performing, and as you step through the program, you're performing those operations that kind of construct that whole quilt structure. And our core kind of analogy here is that when we have 2 points that are connected, like in our language, that means that they're on the same piece of fabric, that they've been either on the original same sheet, or they've been sewn together in some way. In future work, we expect that this language will generalize to other soft objects aside from quilts. Like even when we were working on this, there was a lot of thought about three-dimensional objects that can be constructed using a similar type of framework. And we don't explicitly disallow them, so you could use piecework as is and create three-dimensional things, or four-dimensional things. Maybe that's not as desirable. So a very brief introduction to homotopy is that homotopy spaces are things that, are spaces that contain points, and we can have paths between these points that we're looking at in the space. And now that we have paths in our space, we can also have paths between paths, and paths between paths between paths, and infinitely many paths, layers of paths. So as you kind of building upon this concept, there's a ton of mathematical structures that kind of follow from that. Omega topoi, like simplicial sets, CW complexes. We don't need to know about any of those. But there are the things that also use this kind of idea of homotopy. If we weren't using the lowest tech option, we would have a nice animation here showing how when we have 2 points x and y, we have two different paths P and Q between them. And we also have this continuous deformation in the space between P and Q that we're calling R here. And all of this is just a fancy way to say that X equals Y and that P equals Q. Kind of the way that we kind of write this out in notation instead of a pretty picture is we might say that in terms of like in a homotopy type theory way of saying this, we would say that X and Y are of type A, points being an element of a type A. P and Q are of type X equals Y, so their type itself isn't a quality between P and Q. And R is also of type P equals Q. Its type is that equivalence. So the traditional type of homotopy type theory, one-level homotopy type theory, there is no distinction between 2 points that are connected and 2 points that are the same exact point. So like X equals Y and X equals X is like the same thing, even though that might not really be what you think in your head. So so that kind of stems from the univalence axiom, which is also on the slide, which basically says that when we have a function between A is isomorphic to B, that implies that A is equal to B in that type. That's actually an equivalence, and that means that A is equal to B is the same thing as A is isomorphic to B. And you're kind of fuzzing that line between isomorphic equivalence and equality, which is what we're interested in here. For our specific application, we're using two-level homotopy type theory, which keeps those two things separate. We are actually interested in being able to tell the difference between two things that are exactly the same and two things that are just connected to each other, but we still make use of the fact that we can blur those lines when we want to. So here we kind of, like throughout the rest of this talk, like we have definitional equality, which means that two things are exactly the same, versus propositional equality, which things that are connected to each other. Another useful thing in homotopy type theory is the concept of a higher inductive type. This would be another slide with a pretty animation. Unfortunately, we don't have them. But the classical example of a higher inductive type is this circle, where we have a base and a loop that connects the base to itself. And that's how you draw a circle using a higher inductive type. And you can kind of imagine how this would be extended to other shapes as well. So if you have two bases, you can create an edge. And if you have multiple edges, then you can create fabric, which is awesome. And that's what we're going to be using as the basis for our language. So why topology versus geometry? They're both about shapes, and they're both useful to talk about shapes. But the problem with geometry is that you have to get into the nitty-gritty details of where things actually are. And we're more interested in the higher level structure of the quilt itself. We focus on topology, but there are still a few little sprinkles on top of geometry just from design changes throughout the development of this language so far that will probably be eliminated as we develop this work further. So now we can get into talking about what this language actually is. It is called piecework, and it is homotopy type theory for quilts. And the very fundamental objects that we're dealing with in piecework are pieces, of course, pieces of fabric. And there are two kind of main types of fabric that we're going to talk about in piecework that kind of form our quilts. You can have fabric like this red rectangle here. It's one piece of fabric. It's all the same fabric all the way through. And then we also have this, this wheel here where you have multiple different pieces of multiple individual pieces of fabric sewn together, and it's still just a piece of fabric. They're kind of interchangeable, but they're also distinctly different. And that's kind of where the difference between propositional and definitional equality kind of comes in, where we're interested in saying that, yeah, now that we've sewn all these things together, yeah, they're literally the same piece of fabric now. So our basic syntax, we're not going to talk about this too much because it's really just all the things that you would like in a programming language, you know, the usual suspects. But we are going to talk about our interesting ones, which are our sewing operations: marking, cutting, and sewing. So before we can talk about how we operate on them, we can talk a little bit about what our shapes are. Shapes are defined as kind of a collection of edges. This is how you would define this nice red rectangle, who we will be seeing throughout this presentation. The requirements of being a shape are that we have to have at least 3 edges. You can't have a 2-edge shape. That doesn't make any sense. And you also have to be closed in the sense that you don't have any gaps in your edges. It's like the Jordan curve proof, where it's like, obviously it has to be a shape with a boundary. So that's cool. And what we can do with these simple shapes is that then we can form complex shapes, which are, as you can assume, are multiple different simple shapes grouped together in some way. So the way that we represent this is we have a list of shapes and then a list of the substitutions that are of edges, which are used to kind of join them together. So we might say that we're sewing the 3rd edge of S1 to the 0th edge of S2, and that gives us our complex shape, which is the join of this pink rectangle to this blue rectangle. Our sewing operations are used to basically transform our simple shapes into complex shapes, and sometimes vice versa. These are inspired by the types of actions that you would do in the process of constructing a quilt. So no operation, obviously you're not doing anything, you're just leaving your piece of fabric as is. You want to measure your fabric so that you know what your end result is going to be once you actually do something to it. You can cut fabric and you can sew fabric. And those are kind of what most things that you do in sewing boil down to, which is very convenient that it's only 3. That's a great number. So as I mentioned before, we're going to be focusing mainly on the semantics of those 3 operations. So marking. So marking is kind of our equivalent of measuring, and it's how you might want to specify that, oh, I'm going to do this, but I'm only going to do it part way along my shape. What it does is that it divides one of the edges that make up your simple shape into 2 edges at some ratio n. And this is one of the places where those kind of more geometric things come up. It does not actually cut the fabric in any way. It just kind of produces this extra edge that you can then use to perform a more complicated cut or sew that you wouldn't have been able to do using the existing edges of the original shape. We have a little simple algorithm here, which basically, because what we do is we start with just the beginning and the end point of this edge, and then we create this one in the middle. We have a little algorithm here that basically just calculates the distance in between them and splits it at this, and that's where you decide you're going to put your new point. But it doesn't, so it's just a simple, what's the word? Just algebra to kind of calculate that, which is very nice. If we had animations, this would make a little bit more sense. But cut is now what we can do once we have that kind of midpoint split. So if you see that if we originally started with this pink rectangle and then we marked the edges, the top and the bottom edges, we could then cut in between them to create 2 new smaller rectangles based on that original shape. What it does kind of semantically is that it creates 2 new edges and divides the existing shape into 2 new shapes. One very important note is that the points that are being cut between must be propositionally equivalent. So you can't cut between a point on one shape and on a completely different separate shape, because otherwise you'd be cutting in empty air, and that doesn't make any sense. So that is one strict rule that we have here. And the cut is really where this topological approach shines, because when you think about cutting through empty space and avoiding it, when you have a geometric approach, then you have to worry a lot about those kind of non-convex shapes and where you have empty space in the middle of if you have empty space in the center of a piece of fabric and stuff like that. So for example, this might not show up as well. But if you can imagine a shape that has, here you have a pentagon, and you can cut between point 1 and point 2 easily, right? That just makes sense. But imagine if instead this corner here was like down here. That wouldn't be as good, because now you have if you're cutting a straight line, you would go through empty space, which we wouldn't really want that behavior, and that's kind of one of the pitfalls of geometry. So that's why this is like really the place where we love topology. Topology is our friend. And then finally, their last main quilting operation is sewing. Sewing is probably the most simple, because anytime you have 2 edges, you can just sew them together. We're not concerned about lengths of edges. We're not concerned about where they are, if they're on separate pieces of fabric or not. you can just always sew two edges together to form a new shape. And again, this would be very cool with our animations, but if you started with two rectangles and sewed their two edges together, like we saw in our complex shape example, you would end up with another rectangle. This is always how we create complex shapes, is by sewing two edges together. Our main cool theoretical result is that cut and sew are conveniently inverses of each other. The homotopy type theory community uses quasi-inverses instead because you have to show, you have to find the specific way that they are inverses of each other. You have to find that exact specific case. And the really convenient thing is that when you kind of compose the cut operation with the sew operation, you always end up with the same shape as before, albeit with a new seam in it. And same for vice versa. If you sew two things together and then cut that exact new seam, exact edge, then you end up with the same two shapes that you started with. So that's very awesome. That's very convenient because that's exactly what you would expect to happen in real life, and it matches up with our semantics. For future work, we desire to have a type system. We've started some work on it, but it ends up with some kind of confusing and complicated syntax because you have to say whether or not something is already in. There's distinctions that we would have to develop a little bit further, like whether or not something is already in the shape versus not in the shape for some of the operations. Our work, right now it's a kind of imperative programming language, which is not great. They're going to change that probably going forward. But luckily, there is going to be a going forward because the grant got funded based on this work. So that's awesome. I also must thank our quilting consultants. I'm a knitter, not as much a quilter, but we had some very awesome help from some quilters at WPI who were able to provide insight into the terminology and all of that. That was useful for learning more about quilts and what we should do with them. But yeah, thank you. Any questions? Ooh, lots of questions.
Thanks so much, Joshua.
Yippee.
Lots and lots of questions. So just for a variety's sake, I'm going to start from the very back of the room and go forward.
Mm-hmm.
That was cool. Thanks.
Yeah.
Are you allowed to sew two edges of the same piece of fabric together?
Yes, you can make a cylinder
or
or
like Klein bottle.
Yeah.
So, what does that mean for quilting, though? I guess
it kind of doesn't mean anything, I guess.
Okay.
So because our goal was to be as inclusive as possible, really we want it to be inclusive. We kind of the opposite of approach of most programming languages. We really don't want to exclude much, if anything. We really want to enable the representation of as many different ways to sew fabric as possible, even if they might not be physically realizable. So that's kind of our approach so far. We might get more restrictive as time progresses, but not at the moment.
Hi.
Hi.
I've got two questions, but the first one's just been asked, so that's really convenient. So the second one, when you sew edges together, you say you don't care about the lengths.
Yes.
They just sew. But when you cut them, you are caring about the proportion. Why do you do that? Why not just make another point arbitrarily, sort of topologically in the middle of another edge?
So that's I think I said at the beginning, we kind of went through some design changes as the language evolves and over the course of the year that I was working on it. And that's kind of one of those things that we were slowly kind of removing, but weren't quite able to get the finishing touches on reworking by the time that we had to submit for this conference. But it likely would not be it's not going to be part of future work where you don't actually care where the point is. Yep.
Super cool work. I was curious, you mentioned sort of changing the flavor of language away from imperative, but boy, cutting something into two feels pretty imperative to me, right? Like the old thing is gone, you can't use it no more. So I guess, it seems like there's something about linearity here that would be super interesting. I don't know if you've thought about that in the type system. And I guess the other thing I was wondering if you could comment on more is this problem of referencing. Because once you cut, your references all might change. So how do I preserve, the accessibility of references as a program evaluates?
So to talk about the references first. We generally in the semantics and in the full paper and in my thesis, there's like very strict rules about the order of edges as they appear in a shape. And when you cut a shape, there's a very specific order maintained. So the names of those edges do change, but it's predictable. So that's how we kind of manage that. And then in terms of why we're changing away from imperative is because it was originally supposed to be logic programming, and I wanted it to be imperative because I feel like that's how quilting makes sense to me, as like how you would actually do it. But I think the future goals for this work are to kind of have it be more like generative and being able to, instead of necessarily modeling quilts that already exist, but being able to programmatically generate safe quilts.
If you want to reason about these fine-grained notions of equality and also want something logic programming languagey, there's been some recent work on combining equality saturation with data log that might talk to those authors.
Yeah. I have heard much about it.
Is there an inverse to the mark operation? So you put a pin in and then you can take it out?
Unmarking it? No, we don't have an inverse. I think we could add one, but there's not really a super strong reason to. If you wanted to see, if you had something marked and then you kind of wanted to unmark it, effectively all you would need to do is just sew, there wouldn't really be a reason to unmark it unless you were trying to sew it to a whole edge that you had previously marked, but you can still do that by marking the other edge as well. The way it works out is that it doesn't super matter. Yeah.
We're going to have the next speaker set up, but we're going to keep taking questions.
I'm just going to make...
Sorry. Hi, Audrey So, University of Washington.
Yeah.
I'm just curious, great talk.
Thank you.
And also, I think it's so important to be talking about these things that are traditionally very female oriented.
Yeah.
Within this space, I really appreciate the work, and also the work that's being done in this workshop in general.
Yeah.
But I was just curious, what kinds of types would you want to add, or that you want to add to this to the language?
So the main thing is having really rigid, actual types defined for those main simple shape and complex shaped objects.
Okay.
The whole thing, everything is a shape. There's no way to get out of that. So all of it's simple in concept, hard in practice. But yeah, we were mostly focused on the semantics, just because what does it even mean to cut a piece of fabric?
Yeah.
Yeah.
Ron Minsky, Jane Street.
Hi.
Hi. So fun talk. I'm curious if you have ideas for the future of the project, how one of the nice things about having a kind of computational representation of something is that you can then do something with it, right? And I'm kind of wondering, it seems like if the goal is to have a language that's designed that lets you describe things that are maybe not physically realizable. So one thing that maybe I guess you don't do from there is go from the high level design to compile down to a thing you could feed to a quilting machine.
Yeah.
So I'm wondering, what do you want? What are the ideas of how to kind of take advantage of having this kind of computational representation? What do you do with the?
So one thing that we were thinking of is that there's a few other people at WPI who do more quilting related work, and some of them have created tools for digital design, and which is very popular among quilters. Quilting itself is a very manual task. There is no obviously you're using a sewing machine, but you're not automating sewing the pieces together. That's not really something that happens. So what we're kind of thinking, the kind of application that we were thinking of is using this type of model as the back end for a quilt design tool. Digital drawing, basically.
We're a little over time, but I'm just going to keep taking questions because we were late for tech.
Yeah.
It's terribly sorry to Steven. Hi.
Hi, Katie Casamento from Portland State University. I had kind of one observation and one question, both about the equality, which is, and also, as everyone else said, really cool talk. The one observation is you talk about the conversion from a propositional equivalence to a definitional equality.
Yes.
That sounds like the J eliminator. If the standard sort of like eliminator for a propositional equality type gives you sort of a scoped conversion from propositional equality to definitional equality. So that was just kind of an observation that seems related to kind of like in a traditional dependently typed language pattern matching on your propositional equality to reduce it to REFL, and then in that context you've got a definitional equality.
Yeah, in like the full paper, we did talk. I talk a little bit more about how you kind of go from like a complex shape that has a ton of different subshapes in it to being like, actually, I don't care about the subshapes at all. What is just the outline?
Cool,
So,
yeah. And then the other question, which is pretty vague, but is I've got several different kind of intuitions for propositional equality, and a brand new one here is as kind of a separator between two other spaces. That you've got this propositional equality that is like a boundary between things. And I'm just curious if you have anything to say on that intuition sort of in other settings as well. The idea of an equality as a boundary or a separator or something.
So I think something really subtle is that most of the time within a complex shape, there's actually two edges there. So it's more of like you have, I guess, a hole in a space. That's another space inside of it. And then it's it happens to be right next to another hole of whatever. And we're saying that these edges kind of line up to each other, but there is probably actually some kind of, I guess, material in between them. So I think that's, I don't really know if it really, I don't really think I have a ton of insight for you about how that actually like works in other contexts, but the way that I think about it is mostly that you have kind of a seam, like an actual physical seam. Like if you look at your clothes, you have like a kind of a lump or a bump where you've sewn two pieces of fabric together, and that kind of how you set, even though it's it's definitively made out of the pieces of fabric that were sewn together, and it's not anything different, but it's also not the same. So
yeah, very interesting. I'm gonna have to ruminate on equalities as seams. Thank you.
Yeah, no problem.
And with that, I think we'll move on to the next talk. Stephen and Aditi are doing a co-presentation. Because of that, I'm going to hand you guys the physical large microphone so you can pass it between each other very easily. Thank you both, and I think we're about ready to start the talk, so stop your side conversations.
Hi, everyone. Good afternoon. Can you hear me? Okay, perfect. Oh. Okay. Hi, everyone. Good afternoon. My name is Aditi. This is Steve. Fun fact, we're actually meeting in person today. We've never met, and this work has been going on for a year. So it's really exciting to share what we've been working on. So just some contextual background information. I'm a physician in family medicine, and I have an interest in genetics. So this story kind of starts off in 2016 when I went to India to study rare genetic diseases. And Alia, pictured here, she's 2 years old. She's not a result of bad parenting. She is morbidly obese because she has a rare genetic condition. And the thing with rare genetic conditions are they are disproportionately, there's not a lot of medical knowledge that goes on because doctors are trained, we're trained to study more common conditions. Additionally, pharmaceutical incentives, because pharmaceuticals want to make money for, most people, the amount of research and funding that goes into rare disease treatments is very limited. And lastly, and I think the most important thing, is the burden and isolation that comes with a rare disease diagnosis. So that's kind of, my mission as a physician is not just to build connection in the clinic, but outside to sort of bridge the gap between rare communities and the common public. And so you might be wondering, how, if I don't have a rare genetic disease, why should I care? So in 2019, there was a landmark study done that analyzed the economic burden of rare diseases on the U.S. economy, and it came out, they the estimated burden was about $997 billion. That's per year. And they only used around 335 rare genetic diseases. And for context, there's over 7,000. So that's just a very, very small sample of kind of what we're looking at. So I think it affects, hopefully, the study kind of remarks the importance that it affects all of us, even if we are not diagnosed with a rare condition. And so I like to do a lot of writing and music, and I came across Stephen's work I think I do a lot of searches for music and genetics, and so my YouTube algorithm kind of passed on a video of Stephen's work, and I reached out to him and I said, hey, can we create something that kind of encompasses rare genetic music? And so we took, in this study, the way that the study was divided up, there were different rare disease groups. So like diseases of the digestive system, diseases of the skin, and we kind of transpose this. I don't know if you're familiar, the Indian musical system, they have a Carnatic music system, and there's 12 different ragas, which kind of form the base rhythm to each of the, like one of their subsystems. And you can essentially kind of translate the words in Sanskrit to bodily systems. And so, for example, Netra means eye. And so we used that raga for all the eye diseases. And I'm going to pass it on to Stephen, and Stephen makes the magic happen. So here you go.
So this turned out to be kind of an exercise in turning spreadsheets into music. And so I thought I would start off, if I can figure out how to get out of this. There we go. So this is the spreadsheet that Aditi sent me. Oh, I have to eat the microphone. This is the spreadsheet that Aditi sent me. It has 230 diseases with their promoter sequences. And so Aditi's idea was to use the promoter sequences as a kind of calling card for each disease. I thought I would start off by showing you something simpler. This is just a chain of amino acids. It's one of the proteins from the coronavirus, and I got interested in this a couple years ago. So I thought I would play one of these for you. Except I have lost entertainingly. Oh, great. Hold on. Sorry, folks. Oh, here it is. Nope, it's not. Curses. This'll do it. All right, so if you just take one of those very simple spreadsheets, it's a one-dimensional thing basically with one extra column marking secondary structure, if you know what that is. And so here's what one of those sounds like. And of course you can map them all sorts of ways. Here's another mapping. Where the basic idea is that if it's a hydrophilic amino acid, it likes water, and so I gave that a higher register. If it's hydrophobic, it doesn't like water, and I give that a lower register. And then the secondary structure, the beta sheets have a little gyro sound, and the alpha helices have a triangle sound. And when the chain turns to fold into its three-dimensional structure, it changes key, basically. So that's that. One problem that you quickly encounter with this stuff is the problem of scale. In other words, a lot of these things are very long. One of my favorite examples for this was a sonification I did several years ago of Trump's lies. Okay, so the problem is this was only the first 6 months, and of course there's way more. So I haven't figured out how to solve that problem of scale yet. But I came across a similar problem of scale with Aditi's spreadsheet, because we've got 230 of these things. And so the first thing I did was I wrote a max patch. Is anybody a maxer here? Great. This is a nifty thing that just takes the spreadsheet and separates it out into these different fields. And so if I scroll through it, it's just going through these things. And this is how I ended up making the piece. There's way too many letters of DNA to go through all of them. And so I had the idea to take how many letters you hear are determined by how many genes are present in this disease. And so in this particular disease, there's 9 genes involved, so you hear 9 letters. In the next one, there's only 1. And so this lets you get through the data a lot faster, and it also kind of gives you some variety, and that can be very helpful. But 230 is still a lot to get through. So what we ended up doing was making it pretty strict sonification scheme, but then we decided to interpret it as data-driven music by adding, basically just on top of it, a freely composed electronic viola part. And so let me find that. Okay, so I'm just going to play this for you. Seven and a half minutes. This is the first chakra that Aditi was talking about. Ritu, what does Ritu mean?
I have to look it up. I don't want to tell you the wrong thing, but I'll maybe get back to it.
Endocrine system. Excellent. Then we just transferred into the next chakra, and so you hear the kind of background harmony change. If you follow along with this thing at the top, that'll tell you kind of how far we are through the piece and which category we're in. So that's it. I've got a bunch of stuff I could say about how hard it is to do this kind of stuff, but maybe if anyone has questions first, that's fine.
One, two.
Hi. You mentioned the trouble you had with how long these sequences are, and that you just chose like a couple, or in the case of a lot of genes, many. Did you consider other things? One thing that I was thinking of was like the amino acid coded for or something to try and make the whole sequence shorter.
That's what that is, actually. Those are amino acids that I'm doing there. Oh, you mean in this one?
Yeah.
Well, this is a promoter sequence, and so it doesn't actually code for amino acids.
Oh.
It's like, I think they used to call it junk DNA, but then they found out it actually does stuff.
Oh, interesting.
You okay? Thank you. That was fantastic. Can you talk about choice of instrumentation?
Oh, yeah. So one of the nice things about me, a music professor, is that I know all sorts of awesome musicians. We have one here sitting at the rear, the amazing Gloria Cheng, who you can hear tonight at the free concert, so you should all go. This particular person was Rudolf Haken, who is our electric viola professor at the University of Illinois. And actually, I have to say, writing this viola part was one of the hardest things I've ever had to do. I pretty much gave up in August, and I decided that it was going to be impossible to write anything to go over this. And then I finally started thinking maybe it was possible. And so I finished it, I think, last Sunday. And then I emailed Rudolph and said, hey, mind if I come over and record you? And so he was a sweetheart, and so he recorded it Monday.
Thank you.
That was, thank you. That was beautiful, very haunting. It's kind of terrible to imagine like each of those was just like behind that they were like people whose lives, were really affected by those diseases. I was curious. I know like this is probably this is a really interesting because it's similar, I think, to visualization, but it's like a sonic audialization, I guess. And I was wondering if you considered using other channels to encode more types of data. So like I know this would probably throw the musicality all away, but like for example, if the volume was related to like how many people were affected by that disease or so on, and other types of information that you could encode in these sequences.
I kind of think Aditi should answer this one. So it is called sonification, and there's like a big kind of raging debate over whether this stuff is sonification or data-driven music. And I consider it kind of like a teeter-totter, if it's really meant like a Geiger counter is a sonic device for saying how much radiation there is. It doesn't sound very good, but it's very effective, And this is more like an artwork, but hopefully if you know the mapping, you can infer quite a bit about it, just from listening. But I think connecting it to the human is there's just so much data to get through that it makes it hard. And Aditi had some kind of interesting ideas on that.
Yeah, so one of the ideas is if you think about the DNA sequence, there are just 4 bases, C, G, A, T. And then if you think about the musical scale, you have the letters C, G, and you can kind of transpose that as a musical note-taking system. And you can take essentially whatever DNA you want and then put it to these chords and then use it as chord progression, essentially. And that's like what I am trying to do with a community in New Mexico that is affected by a rare disease. And so a woman whose husband, who has this rare illness, she's penning the lyrics to the song, and then we kind of encompassed like a melody from that disease. And I think it really can restore agency to kind of a forgotten community. And yeah.
Oh,
thank you.
Sounds like a beautiful project. Yeah, thank you.
This is how I got the scales, if anyone's interested. It's in this paper. One of the great things about these 72 Indian ragas is that there's 4 notes on the top and 4 notes on the bottom. And so the 4 notes on the top I just turned into the DNA letters. And the 4 notes on the bottom became the chord underneath it. So that worked out pretty neatly.
Oh, thank you. That was a wonderful piece. I had a couple quick questions. One is you had the electric viola player, but was the other pieces also recorded by live musicians, or were they sampled, or?
Everything else was in the computer. The only live thing was me basically scrolling through the diseases. And this actually made it really difficult because when I wrote the viola part, I realized I had to kind of transcribe the electronics, which are here. But since I did not do it in time, I was just kind of hitting it when I thought it was a good time to go to the next one. There's no click track. There's nothing. It's like hell to try to play with the tape. And so that sucked.
Well, that actually leads in my other question is, maybe I missed it, but how did you order these things? Was there some logical ordering, or?
Yeah, so we took the study that I had showed earlier. They had already categories. They had already categories for like digestive system, chromosome system, metabolic conditions. And so we used that as a framework to kind of transpose it onto the Indian Raga system, because the Indian Sanskrit words, they kind of are a little bit more similar to these, if you can interpret it in some way. Like, for example, Netra chakra is the eye, and so we corresponded that to eye diseases. And that's kind of, and then we use that raga from the Netra system to put it for the eye condition. So that's kind of the framework we used.
So this was beautiful. I assume also part of the purpose of this is to raise awareness of these rare genetic diseases. So my question is, what are some of the important things you want people to know about rare genetic diseases? Like, are there ways that people can help? Is there things that you want policymakers to do? Like, what,
Yeah,
what's your message?
There's a lot of things that can be done for the rare community. I think one of the biggest things is, for me at least, and what I've seen, is the isolation and stigma that comes with a rare diagnosis and sort of surrounding disability. And so being available for someone with a rare condition, I think, is my biggest ask for people, because that can go a long way, even more than money sometimes. So, yeah.
Hi. Echoing what other people said, it's hauntingly beautiful. It's really a wonderful piece, and I think that is certainly kind of enough to give it a reason for existence. But I'm also kind of curious. I have not done any work in medicine, but that seems like a lot of data to keep track of in your head as a practitioner of medicine. Is there also kind of any potential application for like mnemonics for helping people kind of remember the mappings of this information?
Mnemonics. So like for certain diseases?
Yeah, so sort of, I guess I imagine that, if you're going around talking to people and diagnosing rare diseases and things, you're kind of keeping a lot of this information in your head or in notebooks or something. And I'm wondering if it might be kind of easier to remember or recall that with sort of, musical mnemonics to help recollect. I remember this disease sounds this way, and I see this symptom and I hear this sound in my head, and that kind of reminds me of this disease or something.
Yeah, that's a brilliant idea. Right now, the first thing that comes to mind is sort of the heartbeats, and so there's different like murmurs that we kind of can classically use music, and there's, I think, one paper that has like the musical notation, and then S1 and S2, which are the heartbeats, and the different murmurs that correspond to this kind of rhythm. But you bring up a brilliant point to sort of, how can we use musical notation to remember the constellation of symptoms that go with each disease? That would be really cool.
Yeah, it's kind of reminding me of when they had me sing a song about the planets when I was very small to remember the planets, and just at a much more data.
Wow, yeah.
Thank you.
Thanks.
Hello, beautiful presentation. I was wondering if you were considering adding vocals, and how would you execute that? Would you recruit someone who has experience singing, or would you use vocals of the people who may be affected by these diseases to make it more personal? And I just wondering if you were.
So one of our other collaborators, Casey McPherson, his daughter is diagnosed with a rare condition, and he's kind of used the same framework to take his daughter's genetic sequence and put music to it, and he does the vocals himself. And I don't know if we have a sample of that. No, okay. But you can kind of look up his work, and he is, he's put his own experience as a father into the music, into the musical lyrics as another layer of expression. I don't know if that answers your question. Yeah, okay.
I'd add just a tiny bit to that, and kind of responding to you too. I think maybe one of the drawbacks with this approach is that you have a bunch of DNA going, but I see the diseases go by, and like cystic fibrosis, I sort of know what that is, but a lot of them I don't know, but they all kind of sound similar because they're just a bunch of DNA letters, And so I think that's maybe one drawback, but maybe in some ways that's good because these are all terrible, terrible things. For vocals, Casey is a rocker. He's a popular musician. I call this unpopular music, It's opposite of pop music, but we are maybe going to try to get together with there's an orchestra made up of doctors in in Boston, and we're going to try to do some kind of show.
Hi, this is not a question, but rather a suggestion to the recent question about what would be a call to action, and maybe it's not of general use to the people that you're exposing your material to lately, but I think because we're here co-hosted with ICFP, it's worth saying that some of us work on science for rare genetic diseases, and like there's a workshop tomorrow on declarative medicine. I'm presenting a paper there, and I work with a team at University of Alabama Birmingham with a open case review process where every Monday morning anyone who's interested can come learn about what are diseases faced by real people that are coming into our system, and like how we try to help them. That's it. Thank you.
Mm-hmm.
Well, thank you. That was incredibly interesting, and thank you for all the great questions. Let's thank the speaker. Yes. That is actually our last talk of the Daytime Farm program, but don't worry, we continue after dark with the 7:30 p.m. performance, including a keynote by the wonderful Gloria, who's here. Please tell your friends and family that they are welcome to come. It is free to all ICFP attendees, even if they are not at Farm. It is also free to everyone else too. So anyone in the community can come and enjoy. Thank you all for coming.